Hi everybody, I hope you can hear me well. Write in the chat if there are any problems. I think this time it should be better in all ways. I tried to improve some little things. Yeah, so there's a comment that one of the problems from the previous contest was solvable in quadratic time. That's true. The previous stream we had a very basic implementation of fast Fourier transform, so it works really slow. And of course, in some implementations, like that problem had n log squared n time complexity, and then it's kind of hard to distinguish that from n squared, because that n log n that we implemented last time was more like, in real life, it was kind of closer to n squared of n, and then n squared of n log n is hard to distinguish from n squared. But it was just a educational contest. This time, we're going to make our fast Fourier transform 10 times faster, and then the problems that you can find in the contest that is now in the description, there I'm pretty sure you cannot solve them in n squared time. Most of them have limitations like 10 to the 6 and rather small time limits, so this should be okay. Okay, great. I hope everybody's ready. Let's start this stream. So the recording of this will be available on this YouTube channel where you're watching this. The notes that I'm going to be doing, like I'm going to be drawing here, this is also available. You can look in the video description, along with a lot of materials that are relevant to our stream, other videos or articles online, etc., that I used to prepare and are just relevant in general. Also, you can find a contest where I would definitely recommend solving problems, right? So listening to what I'm saying is important, but the most important part is always solving a bunch of problems. This time, I tried to include a bunch of different problems of different difficulty, and I hope that they will spark more of your understanding of how this algorithm actually works. So you first need to register in the group, and then you need to join the contest. During the lecture, I will again mostly answer questions that are relevant to exactly what I'm talking about right now, so that we have a clear recording. If you have some less relevant questions, I can answer them at the end. And also, I would like to remind you again that these streams are not supposed to be watched in any sequence, right? So the first one was for complete beginners, people who have never heard about FFT. And this one is for people who already know about FFT, have solved a bunch of problems on it, like maybe not a bunch, but some. So they understand kind of how it works, and they have some understanding of where they're lacking some of the understanding. Sorry about this. And then they can improve this understanding and also bring more techniques that could help you solve the problems, right? And if we're talking about the last lecture, the third one, then it's a completely different story. That lecture would be for people who have solved, I don't know, like 100 problems on FFT. They understand how to use it, but then maybe they haven't went into some very deep levels of how it works. So from what I said, implies the fact that this lecture is focused on more higher rated participants. So I would say that 1900, 2000 plus Codeforces rating is the person I'm going to be talking to. Obviously, you can join regardless of what's your rating, but that's the audience that I'm keeping in mind. I hope that's everything I have to say at the beginning. And now I think we can start, right? So today we're gonna talk about FFT, but on the intermediate level. First, because I don't know, maybe you've heard about FFT like a year ago or 2 years ago, right? And you kind of understand how it works, but you don't remember the details. So first, we're going to try to recap what exactly FFT does. And when we have this already revived in our heads, then we're going to be able to actually improve it, right? Because if we don't really remember what the algorithm is, it's going to be kind of hard to improve it. Okay, so the first, like, I don't know, 30-ish minutes are going to be a recap of how to solve this problem in n-log time, and then we're going to improve it. So the problem that we're solving is convolution, right? So we have two arrays, P and Q, of sizes n, and we're trying to find an array R such that Rk is equal to the sum over j from 0 to k of Pj times Qk minus j. This is convolution. Right? So we're summing the product of all pairs of indices that sum up to k. To give you some glance of what we're going to achieve today, at the end of today's lecture, so this is just what basic FFT does, right? And at the end of today's lecture, we're going to be able to solve the same problem, but when these indices, when these values Pj are given to us online, right? So we're given one by one. We're first given P0, then P1, P2, and so on. And when we're given some value like Pk, we should be able to compute R0 and so on Rk already, right? Because R0, Rk only depend on P0, Pk. And FFT does it in offline setting, right? When we're already given both of our sequences, but we're gonna learn how to solve this problem not much slower when P's are given one by one. And after we're given Pk, we already know Rk. But first, we have to solve this problem just in general. The stupid solution is going to work in time O of n squared, just go through all pairs, and we want to solve this problem in O of n log n time, right? How do we do that? So first we're going to just discuss how to do that, and then I can tell you that we're later going to make it 12 times faster. So yes, they are given in the sorted order, right? They're given P0, then P1, P2, and so on Pk. So because otherwise, like if you have only P's, like if you're missing some Pks, Pj's in the middle, you can't find Rk, right? Because it depends on all the previous ones. So the problem is that we're thinking about this problem in a wrong way, right? The first obvious thing that we should do is we should think about these things as polynomials, right? We have a polynomial P of x, which is just sum of Pj times x to the j, and we have a polynomial q, which is the same thing but for q's, and then r, k are just indices of their product, right? P times q is equal to r. So we need to find the product of two polynomials. The product of two polynomials, when they're given as coefficients, is kind of hard, so we're going to change the way we look at these polynomials. We're going to look at them as a bunch of samples. So when I have a polynomial p, we're going to think about it as we have some number x0 and the value of p in point x0. We have x1 and the value of p in point x1 and so on, right? And let's say that like n is the size of these polynomials. So the largest degree of p and q is let's say the largest degree of R is n minus 1. So the last summand is Rn minus 1 times x to the n minus 1. So these are even smaller. And we know that if we have a degree d polynomial, degree d, we need d points, d samples that will uniquely represent what this polynomial is, right? Why is it the case? You can just think that if there are two, you can subtract them, and then you have d roots. But a polynomial of degree, oh no, d plus 1 points, right? A polynomial of degree d cannot have d plus 1 roots, right? So then it means that there was only one such p. And then if you have samples, it's easy to multiply polynomials, right? Because if you have the value of p of x0 and q of x0, then the value of r of x0 is just the product of two numbers. So what we're going to do is we have a polynomial p. We're going to, we'll look at its coefficients, right? We look at the coefficients of q. We're going to transform it into a different representation, right, where we have p of x0, p of x1, and so on, p of xn minus 1. This step will be called FFT. We do the same thing with q. We apply FFT, which is going to give us q of x0 and so on, q of xn minus 1. We're going to multiply them just element by element, which is going to give us the values r of x0 and so r of xn minus 1. And then we're going to do the inverse action, right? Given the values in points, we're going to get the coefficients of r, r0, ri minus 1. And notice that we should be able to reconstruct it at the end, right? So the size of r should be at most n, so that we have enough points. But we should use the same points everywhere, right? No, this is not online. Online we're going to be at the end. Right now we're just recapping how FFT works. Because we need to use the same points, like x0, x1, xn minus 1 should be the same for p, q, and r. We need to start with this number of points. So we should initially start with this number n to be the same everywhere, right? So if, let's say that the size of p was, I don't know, a, the size of q was b, then n should be at least a plus b minus 1. Why is it the case? Well, because the degree of p is a minus 1, the degree of q is b minus 1, so the degree of r is a plus b minus 2, so the size of r is a plus b minus 1. Okay. And also because it's convenient, we're going to solve this problem using divide and conquer. For convenience, we're going to need this n to be a power of 2. So we choose n to be any power of 2 that is at least a plus b minus 1. Okay, and how we're going to solve this? As I said, we're going to do it divide and conquer way. So we'll try to, we have two polynomials of size n that we want to compute in n points. Wait, no. Not two polynomials, right? Now we're talking about this FFT, so we only have one polynomial. We have one polynomial that we want to compute in n points, right? P of size n and n points. We want to break it down into two polynomials, each of size n half, right, in linear time. And then we're going to have our nice divide and conquer structure. How we're going to do that? We somehow need to find points in which evaluating the polynomial p looks similar. And then we can just kind of do less work. Well, the obvious points are negatives of each other. So if you look at p of x and p of minus x, they look pretty similar. So this is like p0 plus p1x plus p2x squared plus p3x cubed and so on. And then if we plug minus x, we're going to have minus x to some power. If this power is even, nothing changes, but if this power is odd, we get a negative sign. So we have p0 minus p1x plus p2x squared minus p3x cubed and so on. And now we want to have two smaller polynomials such that we can use them to calculate both of these values. But for that, we can just separate even and odd degrees, right? We have a of x, which is only even degrees, p2x squared plus p4x to the 4 and so on. And then b is odd degrees, p1x plus p3x cubed and so on. And then we know that p of x is a of x plus b of x, and then p of minus x is a of x minus b of x. So knowing the values of these two polynomials only in the positive x gives us the value of the whole polynomial in both negative and positive. There's one slight problem here, is that we're trying to get smaller polynomials, right? Here we kind of get smaller polynomials, but in a weird way, right? They both have n over half coefficients, but the powers are still large, right? The power of a and b is still n or n minus 1. So we would like the power to also be n half. But it's easy to do, right? You can see that all the powers here are even. So you can think about this polynomial as a polynomial of x squared, right? So let's write a different polynomial. We'll call this polynomial p even of y, which will have the same coefficients as here, but the powers are going to grow one by one, not by two, right? So it's p0 plus p2y plus p4y squared and so on, right? And then we know that a of x is just p even of x squared, right? We put x squared and then it grows like that. We can do the same trick with b, just slightly different, right? These powers are not, let's write one more term. So it's going to be p5 x to the 5. These powers are not even, so we can't just take it out, but you can see that everything is divisible by x. So if we take x out, then we'll have the same thing. So it's p1 plus p3x squared plus p5x to the 4 and so on. And now we'll write the same thing, right? So p odd is going to be just a polynomial that had these odd coefficients from p. So p1 plus p3y plus p5y squared and so on. And then b of x is x times p odd of x squared. Let's put this knowledge into these formulas, right? We know how to get a from p even, how to get b from p odd. Let's use it here. So basically we have p of x is p even of x squared plus x times p odd of x squared. And then for p of minus x, we have the same thing, but just with a minus, right? P even of x squared minus x times p odd of x squared. Great. We achieved what we wanted, right? We had p that we wanted to calculate in 2 points, p of size n, we wanted to calculate it in 2 points. Now we have 2 smaller polynomials that we only need to compute in 1 point, right? In general, if we had n points that were negative positive pairs, right? So minus x, x, minus y, y, minus z, z, and so on. Now we only have 2 polynomials. We have 2 problems of size n half, and we only need to compute them in points x squared, y squared, z squared. So we have twice less points. The problem with divide and conquer here is that we cannot continue, right? Because we had positive negative pairs, we squared, and now all numbers are positive. We can't make them positive negative pairs again. So to do that, we need to use complex numbers, right? In real numbers, this is not possible, so we need to use complex numbers. So for example, let's see, like if we would have n equal to 1, we would only need 1 point. Let's say that this point is 1, right? We can choose the points where we evaluate our polynomial however we want. So let's choose the easiest one. The simplest one is the number 1. On the previous level, we need two numbers such that if we square them, we get 1, right? So we need a positive negative pair, x minus x, such that then when we replace them by x squared, we get 1. So we need minus 1 and 1. These are the points that we use for n equals 2. But when n is equal to 4, we cannot use real numbers anymore, and we need to go to complex numbers, right? Because we need some numbers such that if we square them, we get minus 1 and 1. For 1, it's easy, right? It's again 1 and minus 1. But for I, we don't know how to do that in real numbers, right? We need x squared equals minus 1. But if we use complex numbers, that's not a problem. It's just I and minus I. And then we can continue like that how long we want, right? So for any number n, what we're actually interested in is the solutions of the following polynomial, right? We want the numbers such that if we power them to the nth power, we get 1. right? So let's say that n is like 2 to the k. We're on k levels down. We need to square the number x k times. If we square the number x k times, you get x to the power of 2k, and you want to arrive at number 1 at the end. So x to the power of 2k, 2 to the k should be 1. Okay. So as I said, in real numbers, we can't always solve this, but in complex numbers, all polynomials of degree n always have n roots. They're not always necessarily distinct, but in our case, they are going to be distinct. So we'll have n such numbers, and that's exactly what we want, right? So when n is equal to 4, we need 4 numbers. When n is equal to 2, we need 2 numbers, and so on. Let's quickly recall how complex numbers work, right? So real numbers are given on a line that is called a real line. We have a 0, we have a number 1, we have number -1, and so on. Everything lives on a line. But with complex numbers, we have to introduce another dimension, so-called imaginary numbers. And then any complex, and what are these imaginary numbers? So the analog of the number 1 in an imaginary is just number I, right? It's 1 away from 0, but in the perpendicular direction. And this will be -I. And then any number can be represented with its coordinates, right? It just has some real part A and imaginary part B. And then this number is A plus B times I. So when we think about these numbers, we can do addition, multiplication. Addition is very easy. It's just, what is the word? I forgot the word. Shift. You just shift something, right? So basically it's like adding vectors. Like if you have one number and then you get another number, you just put them together and add them up. Multiplication is a little bit more complicated, right? So we define the number I basically as the square root of -1. So I squared is equal to -1. And then we can do all our algebraic operations just algebraically without thinking about what actually they present. So for example, A plus BI plus C plus DI is equal to A plus C plus B plus DI, right? This is the same as I just told you, right? You just add up the real components, add up the imaginary components, so you just add up two vectors. So for example, adding some number to all the numbers on the plane represents just a shift, right? If I take the number 1 plus I and I think about adding this number to all the numbers, then both components will increase by a factor of 2, or by a factor of 1, right? Not a factor, but 1 will be added to both imaginary and real components. So I'll shift the whole thing by 1 in both directions. If you multiply, we again just use the rules of math and we can just do this by hand. This is not really intuitive. I'm going to tell you how to think about it intuitively, but you can do that, right? So we just multiply everything with everything. A times C is AC. Then we have A times DI plus BCI, and then BI times DI will be BD times I squared. But we know that I squared is -1, so actually this is AC minus BD plus AD plus BCI. Right, you can do this and never think about what this actually means. But I think it's important to understand what these things actually represent. As I said, when you add a number, you just shift everything so that 0 moves to that number, right? If I take 0 plus A, it's equal to A, right? That's obvious. So when I add a number, I shift the plane such that 0 moves to that number. But when I multiply, I do something similar, right? 0 plus A is equal to A, and 1 times A is equal to A. So when I multiply, I want my number 1 to move to a. And obviously 0 times a is 0. So when I multiply by something, 0 should be fixed, but the number 1 should move to that number. And I want to say that it's always just some kind of rotation and scaling, right? I have my number 1, I need to move it to some place on the plane, right? So I need to somehow rotate it and then stretch it. And for that, there is a great animation. I showed it last time, I will show it again, right? So we have this number 1, and if I move it somewhere, it represents scaling, so multiplying all the numbers by this value, right? So I have this lattice, and I multiply the whole lattice, right? And I have this specific number, 1 minus I, that will look how it's changed when I multiply it by something. So for example, if I multiply just by a real number, it just scales everything by a factor of 2. And that makes sense, right? All numbers just are multiplied by 2. I can multiply by 5, it's outside of the screen. The same thing with multiplying by 1. It would mean just rotate everything by 180 degrees, right? 4 will become minus 4, 2 will become minus 2, 1 will become minus 1. So we just do a 180 degree rotation. And then we can combine these things, right? We can rotate and we can scale. And then we can do them together. So if I want to multiply by 2 plus 3i, it means that I take this number 1 minus I and I multiply it by 2 plus 3i, right? I first take the number number 1, I rotate it, and then I scale it. And the same thing happens to this number, right? I first rotated it, and then I scaled it. And this is what complex multiplication actually is. It's a combination of a rotation and a stretch, right? And our stretch is basically the distance to this number z from the origin, right? Because we had number 1, which was okay, I think I have some troubles with internet. Write in the chat if there are some lagging. So I had the number 1, which was 1 away from the origin, and then it becomes the number z. So it means that I need to scale it by the distance from 0 to z, right? And if this number is a plus bi, this is just square root of a plus b squared, right? And then there is a rotation. Because we're solving this equality, let's think about what it means in terms of what I already told you, right? So multiplying by x means this weird thing of rotating and scaling, right? So let's think about it this way. We had number 1, we multiplied it by x m times, and then we arrived, at the number 1 again. Obviously, we get that the number x should be 1 away from the origin, right? Because if we had the number 1 and we scaled it n times, and then we arrived back at number 1, it means that our scaling was always 1. We couldn't, if we would scale by more than 1, it would be more than 1. If it was less than 1, it's less than 1. So we always leave in the points that are 1 away from the circle, right? So there's no stretching. So now it means that all the numbers that we are interested in just live on the unit circle. Sorry, I can't draw a unit circle, but let's think that it's a unit circle. And then all the numbers just represent a rotation, right? If I have a number on a unit circle, it can be just defined by the angle alpha. And then it means that I take the number 1 and I move it here. So basically it means that I just rotate the plane by alpha degrees. And then I need to take some number x on this circle such that if I rotate by that angle alpha, I come back to 1. So alpha times n should be a multiple of 2 pi, right? I need to go back to 1, so I might, the angle of rotation that does nothing is 0, 2 pi, 4 pi, and so on. So this should be of form 2 pi times, let's say, j. So it means that my angle alpha should be 2 pi j over n, right? And this works for every value of j. Yeah, I'm just reading the comments. So any number of this form works, right? And how many of these numbers there are? I want to say that there are exactly n of them, right? I can take 2 pi times 0 over n, which will represent angle 0, so it's just number 1. Of course, 1 to the power of n is 1. I can take 2 pi times 1 over n, 2 pi times 2 over n, and so on. 2 pi times n minus 1 over n. Why is it only n minus 1? Because when I do n again, this will be 2 pi times n over n, which is 2 pi. So I came back to 1. So it's the same as this one. And then we're going to be cycled. So we have exactly n solutions. And these are exactly the solutions that we need. But we wanted not the angles, we wanted the values, right? So what is this value with angle alpha? What are these coordinates, right? We want to represent as a plus bi. Well, this is simple, right? We know that it's on a unit circle. So let me draw it a bit larger. So it's on a unit circle. We have some angle alpha, and this is 1. So what is the sine of alpha? Sine of alpha is this side over 1. So this side is actually just equal to sine of alpha. And this is equal to cosine of alpha. So if we're interested in a value on a unit circle with some specific angle alpha, it's just cosine of alpha plus I times sine of alpha. And given that we know that the angles that we're interested in are of the form 2 pi j over n, the values that we're interested in are cosine of 2 pi j over n plus I times sine of 2 pi j over n. For all possible values of j from 0 to n minus 1. Great. I just want to give you a quick fact that is not very relevant to what we're talking about, but just to let you understand how important this understanding of complex numbers is. So as I said, a complex number, if you multiply it by a complex number, you rotate and stretch, right? And this rotation depends on the angle. So what if I take the number that on the unit circle that has angle alpha, and I multiply it by a number that has angle beta? Then I should get a number with an angle alpha plus beta. So we know that cosine of alpha plus I times sine of alpha multiplied by cosine of beta plus I times sine of beta is equal to cosine of alpha plus beta plus I times sine of alpha plus beta. This is just from what we talked about, right? That multiplying by a number, we had a number with angle alpha, and then we multiplied by a number with angle beta, we got a number with angle alpha plus beta. But on the other hand, you can think about it algebraically. I can just take these two brackets and multiply all the terms, and I'm going to get cos alpha cos beta minus sine alpha sine beta plus I times cos alpha sine beta plus sine alpha cos beta. And note that we know that this value is equal to this one, and this value is equal to this one. So if you know complex numbers, you don't need to remember formulas for cosine and sine. Cosine of alpha plus beta is this, sine of alpha plus beta is this. We learned it by just looking at complex numbers. But that's not relevant to what we're talking about, right? We learned what kind of numbers we should use. And I want to say that now basically our solution is done, right? Let me remind you what we were trying to do. We were trying to do some divide and conquer, right? We had a polynomial of size n. We wanted to calculate it in n points. To do that, we wanted to split it into two polynomials of size n half each and compute it in n half points, right? To do that, we want to always have some positive and negative pairs and then square them. And when we square the numbers, we want the number of numbers to be smaller by a factor of 2, right? So initially, we had our solution of the equation x to the n is equal to 1. And there were n of them. When we replace them by the values y, which are x squared, well, now they are just solutions to this equation, right? Because if y is x squared, then x squared to the power of n half is 1, right? And now there are n half of such solutions. Now we square them again. So z is y squared. And we're interested in solution z to the 4 is equal to 1. There are n over 4 such, and so on. So this will always work, right? If we start with solutions to this equation, then on every next iteration of our divide and conquer, we're going to get twice less values. And what is going to happen at the end? At the end, we're going to have n is equal to 1. So our polynomial is just a constant, and we want to compute it in a single point. This point is 1, but it doesn't matter. Anyway, this value, this polynomial in every point is equal to p0. So its value is equal to its coefficient. So on the lowest level of recursion, we do nothing. Otherwise, we split our polynomial into even and odd parts, and we recurse. And then we need to combine those values using the formula we had. Let's copy that formula, right? We know that p of x is p even of x squared plus x times p odd, and p of minus x is similar. Good. That's the whole algorithm. Let's implement it quickly. Okay? So first, we'll not care about complex numbers because complex numbers are already implemented in C++. So we can use include complex, and then we can make it shorter. So there are complex numbers for any type, right? We have our coefficients a and b. They should be some real values, right? We can use integers, but our values are not going to be integers because there are sine and cosine of some angles. So we're going to use doubles. And let's call this type CMPL for short. And then we can create complex numbers. Like, for example, I can give it a real and imaginary part. It's going to be 3 minus 4i. I can just create a number from one value. It's going to be just a real number, and so on. I can write it even like this. Q is equal to 2. And then I can also I take a number, I can call its real part, and I can also call its imaginary part like that. And then there are obviously, like, I can also do z times t plus q, all these possible arithmetic operations. So let's do our divide and conquer, right? We have f of t, which takes as input a polynomial p, and it's going to return its values in those points that we talked about, right? The points that have form cosine of 2 pi j over n plus I times sine of that value. So let's say that n is the size of p. We always assume that the size of p is in power of 2. If that's not the case, just before we call this recursive function, we just make it to always be a power of 2. And we have our base case. So if n is equal to 1, if that's a polynomial of size 1, so it's just a empty free coefficient, then there's nothing to do, right? I just return p. But now this p means different, right? Now this is a value of this polynomial in point 1, which happens to be the same as its free coefficient. Otherwise, I need to separate my polynomial into p even and p odd. Both of them will have size n over 2. And then I just go through all the indices and I put p even is going to be p2 times I. Let's not use I because I is an imaginary number. Let's use j. And p odd of j is p2j plus 1. Then we just recursively compute the values of p even and p odd in squared numbers, right? So we call vector of complex numbers val even. When not is not even, again, this never happens. I always think that n is even. For that, before I call the function, I make sure that the size of p is a power of 2. If it's not a power of 2, I can just add 0 coefficients at the end. Val even is an FFT of p even, and val odd is FFT of p odd. And now I need to combine them into the values of p. Let's call it val p of n. So we have this formula here, and we can use it, right? Note that how do our roots look on a circle, right? We look at all angles that are multiples of 2p over n. So it's this angle, this angle, this angle, this, and this. And what does minus x means? It means that we negate both our coefficients. So it's a value on the other side of the circle. So it's the symmetric one. And if it's 0, 1, 2, like these are the order of our roots, right? Then it's going to be, if this is index j, then the opposite is j plus n half, right? It should be on the other side of our cyclic array. Let's think that our array is cyclic. So let's say that this x is the root, the jth root that we're interested in, and this is going to be j plus n halved root. So actually we only go through the first n half roots, and while we calculate them, we also calculate minus them, which are these ones. So we go through the first half, we compute what is the x, right? Our angle is 2 pi j over n, and given the angle, we know how to compute our value. It's been a cosine of 2 pi j over n and sine of 2 pi j over n. And now we just use this formula, right? For jth one, we just take this and this. And if you think about it for a while, you can see that this j squared is going to have also index j in our recursive call, right? In recursive call, we have all the angles of the form 2 pi k over n half, because we have twice less values, right? And if we want this to be equal, what should be the value of k, right? The value of k should be j half, right? But okay, we're interested in twice larger angle, right? Because we need x squared. X squared has angle 4 pi j over n, right? It's twice larger. So we want this value to be equal to that one. And then I want to say that if I put j here, this works, right? 2 pi j over n half is 4 pi j over n. And why do I need 4 pi j over n? Because I want to know the value in the x squared. So x squared has doubled the angle. Okay. So actually the indices are just the same. I take also the jth index, and I use the jth index also to compute the j plus n halved value. Good. So val p in point j is what? Val even in point j plus, I need to multiply by x, so it's wj times val odd of j. And for j plus n half, we do the same, but we just subtract. Okay, good. I guess this is the end. We wrote our FFT function. There's a lot of stuff that goes into figuring it out, but at the end, the code is pretty simple. I guess the only problem is that we haven't defined the number pi. Let's define the number pi. Const double pi. I normally do it like this. You can do it however you want. Okay. What about the inverse direction? Well, the simplest way to do that is think about an algorithm, right? So we calculated FFT of our polynomial. We can do it for p, we can do it for q, then we multiply, but then we need to go back, right? And to go back, we need to, given the values, we need to compute the coefficients. So our FFT did multi-point evaluation, right? It evaluated our polynomial with a bunch of points, and now we need the opposite thing, so interpolation. But this is very simple because, so we have the values of r in a bunch of points. R x I n minus 1, and we want the coefficients, right? I want to say that if we would already have the coefficients and we would apply f of t, we would get these values. So now we just want to kind of do the opposite. So let's just imagine that we did this forward f of t from the known coefficients, and now we just want to undo that. Undoing is very simple. Like if I do a bunch of actions, I can just do them in the reverse order. I can just undo them in the reverse order, right? The same idea goes into union find with drawbacks, right? You can unite a bunch of sets, but then you can just bring your memory back to the initial state by undoing all the actions you did, and then you're going to be back. So here, we should just take this function, let's just make it smaller, and then just do all the opposite actions in the reverse order, right? So let's make our inverse f of t that will take as input the values of p, and it's going to go back along this pipeline, and it's going to undo all the actions so that at the beginning we have our p and we can return it, right? So we have n is the size of p. If n is 1, we did nothing, so we again do nothing. If n is 1, oh, it's not the size of p, it's the size of val p. We return val p. Otherwise, we have values of p. From them, we need to calculate the values of val even and val odd, right? So let's make these vectors. Val even of size n half, val odd of size n half. How do we calculate them? When we again go through this cycle, I guess technically I have to go in the other direction, right, from n half minus 1 to 0. But you can see that different iterations are independent of each other, so it doesn't matter. I can just do the same thing. And now I know these two values, and I need to use them to calculate these two values. Well, you can just do some mental math and understand how to do that. You can see that if I add up these two, these will cancel out, and then I will have val even times 2, val even j times 2. So let's take our root of unity again, and let's say val pj plus val pj plus n half. What is this value? I know that this value is the sum of these, so it's going to be val even times 2. So val even j is just a half of this thing. And now if I subtract this from this, let's subtract val pj minus val pj plus n half, then these are going to cancel out, and I'm going to have 2 times wj times val odd. So to get val odd, I just add them up, divide by 2, and then divide by wj. So now I have val even and val odd. Given the val even and val odd, I can just recursively compute our p even and p odd coefficients, right? Inverse f of t of val even. and inverse FFT of val odd. And then I just have all the even coefficients and all the odd coefficients of P. I just combine them together, right? From 0 to n. Again, we're just undoing everything that's done here, right? I put the values of P into P even and P odd. Now I put them back. So P 2 times J is P even J. And P 2 times J plus 1 is P odd of J. And now we return P. Good. Now we have our inverse FFT. Obviously, it also works in n-ogan time. All right, yeah, why did this work in n-ogan time? Well, because it's just like merge sort, right? You have one problem of size n, you do some linear amount of work, and then you have two subproblems of size n½ each. So in total, you recurse, then you recurse again, and then on every level of recursion, your total work is O of n, and the depth of recursion is log n, because we half every time. So the total time we take is n log n. Great. Now everything that's left to do is to write the multiplication of polynomials, right? So we have two polynomials. One is P and one is Q, and we want to multiply them. The result is probably going to be a vector of long-longs, because like you sum up products, so it's going to be like m times c squared, where c is the limit on the values in P and Q. First, we need to find a power of 2 that is large enough, right? We know that, as I said at the beginning, the size of R is going to be like size of P plus size of Q minus 1. So we need a power of 2 that is at least size of P plus size of Q minus 1. And while it's not true, they multiply it by 2. Then we put our, like initially we have these vectors as integers, but we're going to work with them as complex numbers. So we should put them into the same, like we're going to have the same vectors, but they're going to be of complex, they're going to be complex vectors. So basically I copy P begin, P end into P complex begin. I do the same for Q. And then what do I do? I need the values of P, which is FFT of P complex. I need the values of Q, which is FFT of Q complex. And then I want to calculate the values of R, which are just going to be the products, right? So for j is equal to 0, g is less than n, R value j is P value j times Q value j. And then I do just the reverse FFT. R complex is equal to inverse FFT of the values of R. And then I just copy them into, like, they are technically complex numbers, right? But because we know that our initial polynomials were integers, we know that their product is also going to be integer. So even though this is a complex number, it's actually just, I mean, if we don't care about the error, right, there's always going to be some error when we work with doubles. But if we ignore that, this number should look like, I don't know, some 5 plus 0i, or like epsilon I, and this is also like 5 plus minus epsilon. R of size m, and then we copy all the values back to R. And as I said, because these values are probably not calculated exactly, but because we know that they are integers, we only need precision up to 0.5, right? We can always round to the closest integer, and if all our calculations were precise up to absolute precision 0.5, we're going to be all right. So we have Rj is equal to round of RCMPL dot real, right? We need to take the real part and round it. And then we return R. Great. This took longer than I expected, but hopefully this is going to be a good good base on which we can do all the work that's going to follow. So I want to say that we learned how to multiply polynomials in n-organ time. Again, remember that probably these values are going to be large, so this should be 1, 1. There's just one simple thing that I kind of put under the rug. So you can see that here we divide. I never told you how to divide by complex numbers. Well, dividing by integers or real numbers is easy, right? If we had a plus bi and I divide it by 2, obviously I get a half plus b half I. But with complex numbers, it's a little bit more complicated. But again, our idea of what multiplication is will help, right? So we know that if I multiply by some complex number, it's some rotation and a stretch. And division is just the inverse operation to multiplication. So I need to do the opposite stretch. So if I had a stretch r, then I need to do a stretch of 1 over r. Makes sense, right? With the real numbers, the opposite number is 1 over r. And if the angle was alpha, my new angle should be minus alpha, right? So that my number goes back. But because all the numbers that we care about live on a unit circle, so r is always 1, we only need to care about the angle. So actually, if you have a number that lives in a unit circle, then 1 over this number is just the same number that is mirrored along the real axis. So if this was a plus bi, if I mirror it, then a doesn't change, and the second coefficient changes its sign. So it's actually a minus bi. And then you can do it also algebraically. I do a plus bi times a minus bi. This is a formula for a difference of squares. So it's a squared minus bi squared, which is a squared plus b squared. And because these numbers live in a unit circle, this is 1. This is exactly what we wanted. We wanted a number such that z times 1 over z is 1. And this operation of mirroring along the x-axis is called conjugation. So you have a number a plus bi, its conjugate, which is normally drawn like this, is a minus bi. Note that it's not always 1 over z, right? It's only 1 over z for numbers on a unit circle. Otherwise, you also need to then divide it by a squared plus b squared, right? Yeah. I mean, this is not the, so this is the formula for conjugate, and if I want to get 1 over z, then I would need to take this number and divide it by a squared plus b squared. Okay. Good. So now you understand if you needed to implement this. Now we just have this conjugate, and it also exists in C++, right? Instead of dividing, you can just multiply by conjugate of wj. Great. Do we have any questions about the basic implementation of FFT? Because from now on, we're going to just start doing optimizations. We're going to write less code, then we're going to do it faster. If there are still any questions about maybe something was unclear, you can ask now. Otherwise, I hope that at least you recode how FFT works. And now we're going to be able to work together to our goal. Great. So this idea of implementing inverse FFT as just undoing all the actions from the normal FFT, that's a great idea. It helps here, and it also helps in many other situations. For example, like here we evaluated our polynomial in very specific points that we chose, but there is also a different problem of evaluating a polynomial in given points. And then the the opposite problem is interpolation, right? Again, given values in specific points, how to interpolate it. And then I want to say that again, if you can solve one problem, you can solve another. Because you could just write code for one problem and just write code that undoes all the action that the first code did to do interpolation. Again, it also works for union find with drawbacks and so on. But we don't want to write that much code. I want to say that we only actually need this function. We don't really need this other function. Why is it the case? Well, I just want to show you something. Let's run Python, because it's easy. And now let's, there is already implemented FFT in Python, in NumPy. And let's call FFT of some array, 1, 2, 3, 4. We got some weird values, right? This j is just I. Sometimes it's just called j in different contexts, more of a like engineer context, or like if you program stuff, I is normally an index, so j makes sense. We got the values of our polynomial in some points. Like in this case, we know that these are roots of fourth power of 1. So these are 1, I, minus 1, and minus I. But what if we do FFT twice? What if I apply FFT to FFT of 1, 2, 3, 4? At first, it doesn't make any sense, right? Because FFT we apply to coefficients of a polynomial to get values. And now we think of values as coefficients of a different polynomial, and we evaluate this polynomial again. Like from the physical perspective, let's say this doesn't make any sense, but let's try to do that. You can notice that all our imaginary parts are zeros. So this is actually an integer array, 4, 16, 12, 8. Do you see any pattern? We had 1, 2, 3, 4, and we got 4, 16, 12, 8. We can do the same thing for 1, 2, 3, 4, 5, 6, 7, 8. Maybe this will help even more. Now we have 8, 64, 56, 48, 40, 32, 24, 16. Do you see anything different here? Anything interesting here? Please write into the chat something so that I'm sure that I'm actually still online, even if you don't know the answer to the question. Okay, now I'm not sure. Yes, okay, good. So you can see that all these numbers are multiples of 8, right? And this is 1 times 8, this is 8 times 8, 7 times 8, 6 sometimes, and so on. So if I divide back by 8, this would be 1, 8, 7, 6, 5, 4, 3, 2. And the other one, right, all of them are multiplied by 4, and if I divide back by 4, it's going to be 1, 4, 3, 2, right? So actually, if I apply FFT twice, it's the same as just multiplying all the values by n and then reversing everything except for the 0th element. But then this means that we already got our inverse FFT, right? Because what is inverse FFT? Imagine that we would have inverse FFT, we have some array P, we have apply inverse FFT, we want to get back to P. But I want to say that FFT itself does almost that. Instead of applying inverse FFT, we can just apply FFT. We would get the initial array, we just need to change it a little bit. We just need to divide everything by n and then reverse the end of this array. So instead of using this tremendous function inverse FFT, here I'm just going to apply FFT itself, and then I'm going to reverse everything except for 0th element reverse begin +1 and then these values are the values of r just multiplied by n. And now when we take it, let's just divide it by n. And now we only need one function. This is absolutely crazy, but it works. But we can't just believe it, so we should prove that, right? To prove it, we need to remember what our FFT does, right? What our FFT does is we have a bunch of values on a unit circle, all values of, all angles of the form 2 pi j over n, right? And we evaluate our polynomial in all these functions, in all these points. I want to say that there is the most basic out of these roots, right? These are the roots of x to the n is equal to 1. I want to say that there is the most basic root, which is 2 pi over n, so j is equal to 1. Let's call this value omega, and I want to say that all the other values are just omega to the 0, omega to the 1, omega squared, and so on, omega to the n minus 1. Why? Again, because how complex numbers work, right? If I multiply by a complex number, I add an angle. So omega to the 0 is 1, then this is going to have angle 2 pi over n, then I add 2 pi over n again, so it's 2 pi times 2 over n, 2 pi 3 over n, and so on, 2 pi times n minus 1 over n. So these are exactly all the angles that we cared about. So actually we evaluate in these points, right? So let's say that we had a polynomial p, and its f of t is a vector b. And now we're interested in what is f of t of b. And we want to prove that f of t of b is almost the same thing as p. Okay, let's just write definition. bj is the value of p in point omega to the power of j, right? Which is sum for k from 0 to n minus 1, omega to the j to the power of k, right? We take like x to the k, where x is omega to the j, times pk, right? And what is omega to the j to the k? It's just omega to the jk, right? Omega to the jk times pk. And we have all these values bj, and now we need to consider the polynomial b, right? b of x, which is the sum x to the j times bj, bj. I'm trying to choose the right indices so that it's not confusing. We have this polynomial, which is weird, right? Because its coefficients are values of a different polynomial in some points. And now we want to, again, evaluate this polynomial in these points. So by definition, c is f of t of b. So cl, let's say, is b of omega to the l, which is sum for j from 0 to n minus 1, omega to the l to power j, times bj, right? But we know that bj is this thing. So it's times sum for k from 0 to n minus 1, omega to the power of jk times pk. Super confusing, right? But let's just understand what's going on here, right? We're just doing basic algebra, just the formulas were kind of large. Now everything's gonna work out relatively easily. So I just want to change the order of summation, right? I want to first sum over k, and then I want to sum over j. So I sum over k from 0 to n minus 1. What do we have depending on k? pk, right? So I have pk times sum over j of what? This times this. But this is omega to the lj, and this is omega to the kj. So in total, it's omega to the l plus kj. Or in other words, you can write it as omega to the L plus K to the power of J. And I want to say that at the end, this is just P, like n minus L basically, right? The inverse index times n. So I want to say that most of these things just cancel out. Most of these things are just equal to 0. Why is this the case? Well, what are these numbers? They are still some of our, like we know that omega to any power is one of our roots, right? And our roots were defined as the roots of this polynomial. X to the n is equal to 1. Let's write it in a different way. X to the n minus 1 is equal to 0. I'm telling you that you can factor something out of here. This is a classical formula. This is just equal to x minus 1 times the sum of powers of x. 1 plus x squared plus so on plus x to the n minus 1, right? Because if you multiply by x, you get all the powers from first to nth, and then you subtract all the powers from 0 to n minus first. So you get x to the n minus 1. So this is 0. And what do we have here? If we think of this number as x, we have exactly the same thing. We have the sum of powers, x to the 0, x to the 1, x to the 2, and so on. And then if this thing is not 0, right, we know that this is 0. So either this or this is 0. So if x is not equal to 1, then this is always 0 for all these powers of w. So we know that if this value is not 1, then all the sum is just 0 and we can just forget about it. So we only care about the case where omega to the power of L plus K is 1. What does it mean? We know that omega to the power of 0 is 1, omega to the power of n is 1, so we take the power mod n. So we want this to be divisible by n. So it's true then L plus K is divisible by n, right? So basically we need K, which is n minus L, but this only works if L is more than 0, right? Otherwise K should be equal to 0, right? Because we need n minus L mod n. And if L is equal to 0, that's n, we don't have n, so we have to take 0. Good, so we know that everything except for one specific index, which is exactly n minus L, goes to 0. And here, what do we have? We know that this value is 1. 1 to any power is 1. So we just sum up n once. So we get pk times n. This is exactly what we wanted. Good. So we learned that CL is just Pn minus L times n. This is exactly what we wanted, right? We wanted to prove that if we take P and apply FFT twice, we get the same array P, just everything is multiplied by n, and we reverse everything except for the first element. There is a different proof of this. So you can also think, what if I multiply all the values in this sum by omega to the power of L plus K, right? Then it would mean that all my powers are added 1. But we know that if I take any of these roots to the power of n, right, it's the same as to the power of 0, because they round about. So I shifted all the powers. So before I had power 0, 1, 2, and so on, n minus 1. I multiplied, so now I have powers 1, 2, 3, 4, 5, and so on, n. But then nth is the same as 0. So actually, when I multiply this thing by omega to the power of L plus K, the sum doesn't change. So if this value was like a, then we know that a times omega to the L plus K is a. There are only two options. Either a is 0 or omega to the L plus K is 1. So we need to consider these two cases, right? Either this a is 0, so there's nothing to add, or the interesting case when omega to the L plus K is 1. Great. We understood that we don't need inverse FFT anymore. Just going to delete it from now on. We only have the normal FFT. We can apply it for the reverse direction. We just need to reverse everything starting from the first index, not from the zeroth, right? From the first one, because we need like going from index I to index n minus j, from index j to n minus j. So our indices are like 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, for example. And now I need this order. So if I sum them up, they should be divisible by 8, right? So it's 0, 8, 8, 8, 8, 8, 8, 8. Just one problem, right? That n minus 0 is n, and I don't have index n, but it wraps around, so it's still 0. So to do that, I need to reverse everything except for the 0th element. And then I just divide all my elements by n. Like technically, I would need to divide all these complex numbers by n, but because I only care about the real part, I divide it by n. Okay, let me recap why do we multiply by n. So we know that at the end, we have this, CL is this formula. This formula adds up some pKs. Most of them are multiplied by 0. If this value is not 1, it's multiplied by 0. But if omega to the power of L plus K is 1, this picture is horrible. Let me write it again. pK times sum over OJ from 0 to n minus 1, omega to the K plus L to the power of J. And we know that most of the time this is 0. But if omega to the power of K plus L is 1, then this is 1 to the J, so this is 1. And I sum up for OJs. So I add 1 plus 1 plus 1 plus 1 plus 1, which is n. So at the end, I get pK times n. This is where the multiplication by n came from. And now we need to undo it, so we need to divide by n to get the values pK. That's a good question. I hope it became clear now. So from now on, because we only have one FFT function, we only need to optimize this one. This will be easier, right? And to actually understand whether our optimizations do anything or not, we're going to keep track of how fast they are, right? This is the most basic limitation of FFT. Recursive, we compute a bunch of cosine and sine everywhere. We have a bunch of memory that we copy. This is crazy. Of course, we can do better. But we need some kind of baseline. We're going to be evaluating the time of this algorithm on inputs of size 2 to the 20. So in other words, so the size of P and Q is going to be at most 10 to the 6, right? Because P and Q are at most 10 to the 6, the actual value of n is going to be 2 to the power of 21, right? Because we sum them up, the degrees of P and Q. So we take basically FFTs on sizes of 2 to the 21, but we do 3 FFTs, right? 1, 2, 3 in total. So the whole multiplication, how much time does it take? I do not include the time that reading the input from the file and outputting the output takes. I only consider the time that this function takes, basically. So our basic implementation, I checked it beforehand. Baseline, let's say baseline. Let's say algo and time. Our baseline solution takes 7.1 seconds. Indeed, what I told you at the beginning, this is basically the time, the time an algorithm that works in n squared of n works, right? N squared of n in this case is 10 to the 9. Probably 10 to the 9 is going to take 5 seconds, something like that. This is horrible. We can make it much better. As I said, we're going to make it 12 times better. So first of all, simple things that we can do. We just copy the vector p for no reason. Let's add a reference here, right, so that we don't need to copy it. And also you can see that we use too much memory, right? We have these different vectors, p even and p odd, like p even and values of even, p and values of p. They have the same size. What is the point of having them? We can just reuse the same memory, right? In the vector p, we can first store the coefficients, and then we can just replace them with values, right? And now it's going to be a function that is void, and it's going to be replace the values in this vector with, so replace the coefficients with the values, right? So we create p even, p odd. Now FFT doesn't return anything, so we replaced p even and p odd with the values. And now we just replace all these val even with p even, val odd with p odd, and val p with p, right? And we don't need to return anything. The code even became shorter. Okay, we don't even need this vector, right? The code became shorter, everything became better. Now here we also calculate it in place, right? So we also get less vectors. Quickly replacing all this stuff. Now we do FFT on R. Looks awesome. We have so much less memory, so much less copying of memory. How much does this code take? Well, so this is pass by reference plus less memory. This takes 4.9 seconds. Significant improvement, obviously, but still pretty long, right? Let's think what in our code probably takes the longest. Obviously, we have this recursion that creates a bunch of vectors, but I want to say that the worst part of this code is this. We're evaluating trigonometric functions n log n times. That's a lot. Like evaluating costs, like even operations with doubles is kind of costly, but calculating cos and sine, that's crazy. But you can notice that these values, they only depend on the value n and j, right? And in our tree of recursion, there are a bunch of nodes when we have the same value of n, right? On one level of recursion, all values of n are the same. So we can pre-calculate it for all levels of recursion, and then we'll only need to calculate n of them, right? For the first level, there are n, then n half, n over 4, and so on. Let's do exactly that. So we're going to have a pre-computation of our roots. We're going to store it in a vector of vectors of complex numbers. So we're going to store for a level of recursion and j. What is this wj equal to, right? How do we calculate that? We have pre-compute w. We take the maximum level as the input, right? The highest level of recursion. We resize w by max level plus 1. And we go over all levels. So we go for levels from 0th to max level. In this case, our current value of n is 1 to the power l. And we resize our vector with n. So we need to have n roots of unity of like 1 over n order, right? So we go through all values of j. We basically do the same thing as we do here, right? Let's copy it actually. But we just save them instead of calculating them over and over again. So WLJ is this complex number. Great. So for all levels, we have, okay, but here we have n roots. For all levels, we calculate these things. And now we just need to replace this wj by wj from our level, right? W level j, depending on what level of recursion we are. Well, we don't know the level of recursion. Let's just pass it for simplicity. We have the level of recursion here. When we recurse, it's 1 smaller, right? And then here we also need to calculate it. So we not only need n here, but also log n, right? Log n is 0, and then log n is increased by 1. And then we just run the pre-computation, right, from this value log n. So in the multiplication, we just initially pre-compute all the roots of unity, and then we can use them. And where do we start from? We start from this log nth level. Great. This made our code much, much faster. But I want to say that there is one more simple thing you can do to calculate even less of these roots, right? So let's look. We have some level, nth level, right? I mean, some level L, and there we have n is equal to n. We calculate all the roots from 0 to n, and let's look into our recursion. On level n, we use w level j, but we only use it for j from 0 to n half. So actually, we never use all n roots. We only use n half roots. So you can actually easily improve the time complexity of this pre-computation by a factor of 2. Just calculate n half roots rather than n. How does this influence our time? So pre-compute roots of unity. This takes 2.4 seconds. We more than halved our time complexity. So obviously this was our bottleneck. There is another way sometimes people do this. As I talked about before, all our roots of unity are just powers of the smallest one, which is the angle 2 pi over n. So here, people just compute the first one, right? W1, which is cosine of 2 pi over n, sine of 2 pi over n. And then in this for loop, we just evaluate its powers. So we store some current w, and then we multiply it by w1 every time. Please never do that. That's horrible. Why is it horrible? Because we n times multiply complex numbers with doubles. Multiplying n doubles in a row will bring very bad precision errors. That's not a good idea, okay? Don't do that. And if you compare the time complexity of this with the precalculation that we did here, there's basically no difference. So our code works as fast as this thing, and it's also numerically stable, which is actually like FFT is a pretty numerically stable algorithm, so even though we work with doubles, that's okay. But if you actually do something stupid, it can stop being numerically stable. And on big inputs, if you do this repeated multiplication n times, that's going to bring big errors. So please don't do that. Cool. Cool. The next obvious step in our improvements of the algorithm is obviously getting rid of recursion. Yeah. So in the chat, we said that we can multiply them, but maybe not that many times, and I'm going to talk about that later. So actually, if you would do, instead of repeated multiplication, if you would do binary exponentiation, that would be okay. But binary exponentiation in this case is going to be bring you one more log here. You can do it differently. I'm going to talk about later how you can improve it even better. Or there is another idea from the chat. You can recalculate it here from cosine and sine every like 32 iterations or something. And then between those, you can just multiply by the first W1. And then it's going to be okay, because you're going to have multiplication of not that many values. Not n, but at most like 32. We're going to talk about something like that later. But first, let's get rid of recursion, right? Recursion is bad, plus we have a lot of memory. like in total we get, I guess we have n memory, but then we include this memory, then we forget about that memory. In total we create n again memory, right? That's too much. Let's think about how our recursive function works. I want to say that there are two different steps. There is what we do before recursion, then we recurse, and then what we do after recursion, right? Think about merge sort. We can implement merge sort without recursion. The reason is that in merge sort we just recurse and then unite. So we can just, instead of recursing, we can just start at the bottom level and then unite back, right? Here we can do something similar, but a little bit different, right? First of all, we're gonna use everything in place, right? So we're only gonna use vector p. We're not gonna create these vectors p even and p odd. We're just gonna, like, basically what this function, what this code here does is reorders the values of p, right? It first puts the even values of p and then the odd ones, and then we recurse on the first half of p and then on the second half of p. And then we first do it recursively, so we, let's look at this. We take the root, we had 0, 1, 2, 3, 4, 5, 6, 7. These are the indices in our initial vector. Now we split them into even and odd positions, right? 0, 2, 4, 6, 1, 3, 5, 7. And then we do it again, we recurse, we put even values, so 0, 4, 2, 6, here also 1, 5, 3, 7. And then finally, the last level, we have 0, 4, 2, 6, 1, 5, 3, 7. Okay? So we first need to just reorder our input in some order, and then after that we're doing basically merge sort, right? We're taking two halves and we're somehow computing the whole thing using these two halves. But we're just not doing merge, we're actually doing something simpler. We're doing this. We just need to understand what is this order that we need to achieve, right? So the order that we're doing is we're splitting the values by the least significant bit, right? We're taking the last bit, and if the last bit is 0, we move that value to the left. And if this bit is 1, we move it to the right. And then we do it again, right? Now we look at the next bit. And if it's 0, so if the second bit is 0, we move to the left. If the second bit is 1, we move to the right, and so on. I want to say that this is very similar to how we would just draw normal numbers if we would have like a segment tree, right? Have a segment tree, and you're trying to understand your positions, understand the index of what is going on, the indices on the last level. You can just think that there are values written on all the edges, and then when you go along the edges, you get the binary representation of your number, right? 3 is equal to 0, 1, 1 in binary. Or like 5 is equal to 1, 0, 1. So here, in this case, we just split them by the most significant bit, right? These are, in the first half, these are the values that have 0 as the first bit. And these are the values that have 1 as the first bit. And this basically just becomes a binary trie. But we just do the opposite. We don't think about the most significant bit, but the least significant bit. So if here numbers are just sorted, it means that in our case, they're going to be sorted by the inverse of their binary representation. So the binary representation of 0 is 0, 0, 0. 4 is 1, 0, 0. 2 is 0, 1, 0. This is 1, 1, 0. 0, 0, 1. What is this? 1, 0, 1. 0, 1, 1, 1, 1, 1. If you reverse these numbers, you can see that it's going to be 0, 1, 2, 3, 4, 5, 6, 7. So we just need to place all the numbers at the position that is the inverse of its binary representation. That's not complicated. You can do it. Like, for example, given a number I guess in log n time, you can just go through all its bits and create the number that it's inverse. But we can do it in linear time using just some dp. Again, there are multiple ways to do that. For example, if you're comfortable with functions like built-in CTZ or the modern version of it, count zeros on the right, you can just pick any bit from this number. You can remove this bit. This number is smaller, so because we're doing dp, you already calculated the inverse of this number, and then you just place this one back here on the right position, which is the inverse position. We're going to do it slightly differently, because these functions, I mean, technically they are okay, but they could take, like, I'm not sure actually if they take constant time by default or only if you include a pragma. I think they take constant time by default, I'm not sure, but even if it's constant, like, it's not the fastest thing, I don't know. There's the dp that people normally do in this situation, which is just to calculate the inverse of some value a, we're going to use the inverse of the value a half. So let's say that we have some number, its binary representation is some string s and then bit b. What is going to be its inverse? It's going to be bit b and then the inverse of string s, right? How could we do that? Let's look at a over 2, right? We're going to get rid of bit b, and we're going to get s here, and we're going to have 0 as the most significant bit. What if we reverse this? We're going to have the inversed s and then 0, right? This is very similar to what we want to get. We just need to divide it by 2 again. So we get rid of this 0 at the end. So we get s reversed 0. And then we add the right bit at the end. We just add b times 2 to the some right power, the largest power that we have. And then we get b s reversed. And this is exactly what we wanted. Let's implement this function. It's not very complicated. So we're going to have our FFT. It's not going to have this level anymore because it's not going to be recursive anymore. Void FFT, vector of complex numbers p. We have n is the size of p. Let's calculate log n. There are multiple ways to do that, but we're going to use the simplest one. While it's not equal to n, we just increase log n by 1. And now we're going to make a vector of bit reverses. So for every value j, we're going to store the reversed version of j. For 0, it's just 0. And for all the other indices, we use this formula here, right? So we take, to calculate bit reverse of j, we take bit reverse of j halved, right? We get this number. Now we need to divide it by 2. It kind of looks weird, right? Because we divided by 2 twice. But it makes sense because when we divided by 2 and reversed, this multiplied our number by 2, right? So we divided by 2, we got here, and now we need to add the least significant bit of our initial number at the beginning. So we need to add j and 1 to the power of log n minus 1. Not to the power, but multiply by 2 to the power of log n minus 1. This is our dp. Great. Now we just need to shuffle our numbers, permute our initial array p, such that every position j goes to position bit reverse of j. But note that if I reverse a number twice, it goes back to the initial one. So actually, I swap a bunch of numbers, right? So for example, here you can see that 0 stays at the same position, 1 is swapped with 4, 2 stays on the same position, 3 is swapped with 6, and 7 stays in the same position. So I just need to do all the swaps between j and bit reverse of j. So I just go through all the positions from 0 to n, and I swap p bit reverse of j and pj. One little caveat, this will not work Just think for a second why this is not going to work. Because I'm not only going to see index j, I'm also going to see index bit reverse of j, and then I first swap them, and then I swap them again. So at the end, actually, this will do nothing to our array. To make sure that our array is actually changed, I should only use every pair once. To use every pair once, I can, for example, say that I only do the swap if j is less than bit reverse of j. Cool. That's exactly what we wanted. Now we just need to get rid of recursion, right? In our recursion, we do the same thing as what merge sort does. So we start at the lowest level of recursion. We need to unite pairs. Then we need to unite subarrays of size 2 into subarrays of size 4, and so on. We just need to understand what this thing does to our array. And it's interesting because, so if we write our, if we don't use more memory, right, then what do we have written? We have p even written in the first half of our interesting thing, and p odd written in the second one. And now we're interested in indices j and j plus n half. They are calculated through indices j in p even and p odd. Jth index is p even is just j half, and the jth index in p odd is just j plus n half, because these are n half elements and these are stored here. So actually we calculate these two values using them, right? We only use these two values to calculate these two values. So this is actually simpler than merge sort, because we don't need any more memory. We can just do it in place. Because to calculate the values of p into indices, we need exactly the values that are stored in these two indices. I hope that's not too confusing, but that shouldn't be. So let's do the same thing that our recursion does, just level by level, right? So we go through all the levels. On the 0th level, we do nothing, so we don't need to consider the 0th level. We go from the first level up to level log n. And on every level, number level, we have these subarrays of size 2 to the power of level. And they are right now split into two halves, and we need to merge these two halves to get the right values there, right? So we do the same thing as here, right? But we need to do it not just for one specific part, but for all chunks of size car n, which is 2 to the power of level. So for all starting points from 0 to n, and these starting points, I add car n to them. So I take the first car n elements, I merge them. I take the next car n elements, I merge them, and so on. So for every car n elements, I need to do like this one step of recursion. Let's actually copy this here and understand how we need to adjust it, right? Again, we go through the first half of this chunk. This chunk we have a chunk that starts from position start to position start plus n minus 1, right? And we need to do something about it. Before we had index pj, but this pj was from the start of our current chunk, but now our current chunk starts not in position 0, but in position st. So we always need to add st everywhere, right? And p even j is again p st plus j, as I already explained. And p odd of j is p st plus j. So this is what we do. And this way we get our calculation. There's one problem. And this problem is that we're recalculating two values using the same values, right? Wait, I did something wrong, right? It should be st plus n half plus j, right? Because this is p even, like, let me draw it first so that you understand it. Like we broke our array into subarrays of size char n. This is our current subarray. This is position start. Here we store p even, and p odd, values of p odd are stored in the second half. So the second half starts with st plus char n half, right? Char n half. Okay. And now we're trying to merge these two parts. The problem is that when we do this, assign this thing, p st plus j changes, but we need to use the old value to calculate this one. So we need to first save these values and then use them, right? So this will be value 1, this will be value 2. So we first compute them and then we assign. Well, 1 p st plus j plus n half is equal to val2. Be careful with that, right? If you use two values to compute two values, you need to store the intermediate result somewhere. You can do this without intermediate variables if you use tie, right? You can just make tuple of these two values and assign a tie of these two things. But it's probably the other way around, right? We take tie of these two things and you assign make tuple of these two values. It's probably going to take more time, I'm not sure, but you can do it in one line. Yeah, that's true. Great. This is our FFT now. It's a little bit longer, but on the other hand, now it's not recursive. And it also uses 0 additional memory almost, right? We only create this vector of integers, and that's it. Because now this function is not recursive, I can actually put our inverse FFT inside it, right? This thing is kind of awkward here. Let's move it back inside our FFT function. So we'll have some kind of flag that says, is this an inverse FFT? And by default, it's false. So if I just call FFT, it's the forward FFT. But if this flag is set, so if we have an inverse FFT, what do I need to do? I need to reverse everything starting from the first position, and then I need to divide everything by n. Let's not use ever index I. Pj divide by n. And then here, what happens here, we don't need to pass this thing anymore because we don't have recursion by levels. And we don't need to do this. We just pass flag true to tell us that we are doing the inverse FFT. And I think this is everything, right? I think we did our FFT without recursion. This should be much faster. What else can we easily change here? There's kind of no need to create this vector R complex. We can just multiply P complex J, like use P complex J, just multiply it by Q and then do the reverse multiplication. This will save us even more memory, right? We're trying to have as little memory as possible. And I think this should be my version of the code that I code no recursion, less memory. It took some work to get to this point, but it was worth it. Now this code takes 1.35 seconds, so almost another improvement by a factor of 2. We're going to just make one little improvement more, and then we're going to have an improvement of a factor of 2 over the recursive version. To do that, we're just going to use our own complex numbers. Because the implemented in C++ complex numbers are great, but they're just a little bit slow. And if we're going to use our own that only implement the things that we need, and it's not going to be, I don't know why actually they are small, so small, but if you implement them by your own, on your own, it's going to be better. So let's make our own complex numbers. We just need a bunch of simple operations. We're just going to store two values a and b. So it's going to be a value, complex number a plus bi. We start by some initialization, right? A of a, b of b. If we pass only one value, then it's a real number. So b is 0. If we don't pass anything, it's 0. Now we implement operator plus, which is going to take another complex number, and it's going to return a complex number which is a plus other a, b plus other b. We can do subtraction the same way. What else do we need? We need multiplication. That's a little bit more complicated, but not that much. Let's remember what is the formula. We multiply the real components, we multiply the imaginary components and subtract it, and then we do the cross multiplication. A plus a times other b plus b times other a. Now we probably need the imaginary and real parts because we use those. And I think that's it, right? I think that's basically what we use. I guess we also use division by a real number. Let's implement that. We're going to return a complex number a over c, b over c. I think this should be enough. Let's see. Create a complex number here, blah, blah, blah. We multiply, subtract, something like that. Here, here. I mean, here we don't have divide equal, so let's just write pj over n. If you have time, you can just add more stuff to that struct that I created. Yeah, I think everything that we needed we implemented. And now, surprisingly, if we use our own complex numbers, this drops to 1.15 seconds. Okay. We already made great progress, right? We like six times approximately we improved our time complexity, even more. But we can do a couple of more things to decrease the time by another factor of 2. So the first simple thing we can do is we can calculate our pre-computation of w of these omega roots even faster. So the simple idea was just pre-compute them, and also the fact that we only use half of them. The other thing is that the roots on the level, the previous level, are also roots on our level, right? Because if we go all the way back to some of the pictures we had, I don't know where, right? You can see that we have 1 and minus 1 here, and we also have 1 and minus 1 here. So all the roots are going to be preserved, we're just going to have twice more, so we don't need to recalculate them. And where does this fact comes from? You can see that if you have 2 pi, and you multiply by j, which is an even number, so let's say it's 2k, and you divide by n. This is the angle that we have, right, of our complex number. This is the same as 2 pi times k over n half. And this over n half comes from the previous level. So if we're calculating some even j root on our level, we can use j halved root from the previous level, right? So actually, if j is even, so if it's odd, we're still going to calculate it like this. But if it's even, we can just use from the previous level j halved value. And these we also don't need to calculate all the time. As I said, all of the roots are just powers of the first one. Let's look at the first one, right? It's going to be first w cosine of 2 pi over n sine of 2 pi over n. And this one is just the previous one times first w, right? Let's write it like this. So the previous one is again just divided by 2, but because it's an odd number, it's going to be minus 1 divided by 2 times first w. Before I told you that multiplying by the first w is a bad idea, if you do it n times, that's going to be a very bad precision. But this is basically binary exponentiation if you think about it. We only multiply log times, right? Because we go to the previous level and then we multiply by something. And because we have log levels in total, every value that we calculate is going to be a product of only log n different values. And that is not bad. If you actually try to implement this and compare, the precision error is going to be small enough that it's not important for our computations. Like, for example, what I'm looking at right now, some source that if we have n 2 to the 20, precision error is going to be like 10 to the 5 times 10 to the minus 16th, which is below what, as I'm going to talk about later, we can even achieve. So this actually doesn't matter. This is going to be okay. And here we only compute like log n different roots. I guess the only problem is that we probably cannot do this for the 0th level, right? But we don't care about 0th level anyway, but we can say that W0 is just 1, whatever. But actually we never use the 0th level anyway. Great. And doing this gives us even more. So optimize omega per computation. This will be exactly 1 second. And one last step that we're going to take is we're going to do less fast Fourier transforms. We already improved our wait, where did this come from? Let's delete this. We don't use it anymore, right? This is our FFT, non-recursive. We already improved it by a bunch. There are still ways to improve it, but mostly this is already good enough. Let's now improve this function. In this function, we have 3 calls of FFT, and I want to say that that's too many. Specifically, I want to talk about these two, because both of these polynomials that we have, P complex and Q complex, they are technically complex numbers, but there's nothing that we store in its imaginary part. So we're kind of wasting space. And I want to say that you can do the same thing, multiply two polynomials, not using 3 FFT calls, but only 2 FFT calls. Why I can do that? Well, let's imagine that we want to square a polynomial. I want to say squaring a polynomial only requires 2 FFT calls, right? Because I need to just compute the values of P, I need to square them, and then I need to do the inverse FFT. So if P and Q are the same, I don't need to do FFT twice. So actually, if you square a polynomial, you only need 2 calls to FFT. And we want to multiply P times Q. I want to find some polynomial A such that if I square it, I can somehow extract the product of P times Q out of the square. Just think about it for a second. What should be this polynomial such that if I square it, somewhere in this polynomial, I'm going to have P times Q. The idea here is, imagine that we have just numbers, I don't know, x and y. If I take x plus y and square it, we know that it's going to be x squared plus 2xy plus y squared. And here I have this x times y. This is exactly what I want. The problem is that Well, to know xy, then it means that I need to know x squared and y squared. But because we live in complex numbers, we can put I here. And then if I take x plus iy squared, this is going to be x squared minus y squared plus 2xyi. So actually the imaginary part is going to contain only xy. So I can then take it out. So I'm going to define the polynomial a to be p plus qi, which is just every index, like every coefficient of a is just pj plus qj times I. Here you should be careful because the sizes of p and q are not necessarily n, so you need to put 0 there if this doesn't exist. And then I take the square of the polynomial a, right? I take a squared, and it's going to be p squared minus q squared plus 2pq times I. And because p and q were real polynomials, this is going to be real, and this is going to be imaginary. So in the coefficients of a squared, we can take just the imaginary parts of all the coefficients of a squared, and I'm going to have the coefficients of 2pq. And then I can just divide, right? So what I'm going to do is I'm going to have only one vector a, and I'm going to put all the coefficients of p and q into a. So, okay, again, we're not using index I, we're only using index j. It's a complex number with the real part pj and the complex part qj. But these could not exist, so we need to check g is smaller than size of p, otherwise 0, g is smaller than size of q, otherwise 0. Then I just make FFT of a. I multiply a by a, right? I square a. I get back my a, right? And now I know that I need to take now not the real parts, but the imaginary parts, and I need to divide them by 2. And now they're going to be the coefficients of p times q. So I didn't actually go into how our FFT works. I only considered the outer level, right? I only thought about it in terms of multiplying polynomials. Just a squared contains our product that we need, so we only need 2 FFT calls. And also see that this also improved our memory situation, because complex numbers, that's crazy, right? We have 2 doubles. A double is a 64-bit bit number. We have 2 of them for a complex number, so that's like basically 4 integers. And here I decreased that amount by a factor of 2, which is also a great improvement. And doing this actually brings the time of our algorithm, right? We do use only 2 FFTs. This brings the time complexity of our algorithm to 0.6 seconds. So we went from 7.1 to 0.6, which is a 12-time x12 improvement. Great. Do you have any questions about improving FFT? I want to say that this is already pretty good. I think 99% of the problems that you want to solve, with this version of FFT you can do it. There are still more improvements. So for example, there is an improvement where, like here, we multiply 2 polynomials using just 2 FFTs. But actually it's possible to do 2 FFTs in 1 FFT. So we do the same thing. We also put p and q into a, but then I can tell you that out of FFT of a, I can take out FFT of p and FFT of q. That's possible. You can think about it as an exercise. How would I get FFT of p and FFT of q if I know FFT of a? This could be interesting if you have not just multiplying two polynomials, but something more complicated that you're doing. There's also a way to do this inverse FFT in an FFT of size half of n, because again, in this inverse FFT at the end, okay, in this case, we actually use both imaginary and real parts technically, but normally, right, we at the end get a real valued polynomial, so we don't use the imaginary part. I want to say that you can still use imaginary part and put a polynomial of size n into a polynomial of size n half. So these are some kind of improvements. There's also something called circular convolution that will put some of your coefficients into the real parts, and then it's going to circle around and put the rest of the coefficients into the imaginary parts. This way we'll definitely use everything that we want. Then you can also, for example, see that we are using these bit reversals. We construct them in every single call of FFT. You can do it once. And then doing this swapping is very inefficient in terms of cache, because this is actually, as far as I understood, this is even worse than doing random accesses to the memory. So you can actually get rid of this. You can just do FFT in place on your memory without doing the swaps. That's more complicated. That's also going to improve your time complexity. Then here we're doing two-wise merge. So we're taking two values and we calculate the two values using that. This is called a butterfly. Like we take two values and we calculate them using them. Instead of having a two-wise butterfly, you can have a four-wise butterfly. This is also going to improve your time complexity, not complexity, but the time of it takes running time. And then you can, of course, use some vectorization. This algorithm is very good, very well vectorizable. It's very predictable and everything like that. And if you do all this stuff, you can make this algorithm even faster by a factor of even another factor of 5 or 10. But I want to say that that's not very important. Like, yes, 7.1 seconds for 10 to the 6 is crazy. But if you work in 0.6 seconds for multiplying polynomials of size 10 to the 6, I think that's enough for 99% of the problems. So I think we're in a good spot here. And that's a reasonable place to finish our improvements of the algorithm. Now we're gonna solve a couple of simple problems, and then we're gonna move to some more applications that we can do with FFT, like multiplying polynomials modulo any number, or doing natural number theoretic transform, or this kind of stuff. So the problems I'm going to talk about now, we talked about last time. I'm not sure if you were here last time or not. So the first one is called subset sum. Basically, you have a bunch of elements, S1, S2, and so on, Sn. And you're trying to solve knapsack, but knapsack without costs. So basically, you want to know for every value from 0 to s, where s is the sum of these si's. We want to know whether it's possible to get it or not as a sum of some subset of these values. How would you do it normally? With a knapsack, it would take s times n time, right? For every element, you go through your dp and you update it. But I want to do it faster. I want to say that I can do it in time s log n log s. How to do that? I just do divide and conquer, right? I'm gonna take my elements s1 and so on sn. I'm gonna split them into two halves. I'm gonna calculate for this half recursively what values I can get, for this which values I can get, and then I'm gonna combine these answers. If I want to get some a, right, some of the elements are gonna come from here, their sum is gonna be k, and some values are gonna come from here, and their sum is going to be a minus k. And now I want to combine those. And this is exactly a convolution, right? If I have some array a that tells me for each value whether I can get it or not, and array B, which tells me whether I can get it or not. If I do a convolution of A and B, let's say multiplication as polynomials, then C will store for every value whether I can get it or not, right? It's going to be sum of AI times BK minus J. If both of them are 1, I'm going to get 1 into my sum. So if the value of C is non-zero, then I can get this value, otherwise I cannot. So on one level of recursion, we have some elements, they all sum up to S, and I run a bunch of FFTs. So one level of recursion works in time S log S, and we have log n levels of recursion, so the total time complexity is S log n log S. Note that I can even find the number of ways to represent every element, because this is exactly the number of ways. But here you should be computing it probably modulo some prime number, because the number of ways is going to be very large. Another simple problem I wanted to talk about is calculating the number of arithmetic progression of size 3. So I have an array, and I want to find the number of triplets that look like A plus X, A plus 2X in this array. How to do that? I'm going to change my representation. Instead of thinking about it like this, I'm going to think that it's A minus X, and A plus X. And then these values add up to twice the middle value. So I just want for every middle value to calculate the number of pairs of elements that add up to 2A. This can be done just using a convolution, right? I just write for every value, from every value that I have, like let's say that my values are from 0 to C. I write for every value from 0 to C how many I have. I convolve this with itself, and this will give me, for every value from 0 to C, how many ways there are to represent it as a sum of elements from my initial array. And then I take every value A from my initial array, see how many pairs of elements can be in a triplet with it. Just be careful that here, for example, AAA is also going to be considered an arithmetic progression, so maybe you should subtract something. Okay, these are the simple problems we had. Actually, I'm not sure. Am I lagging or not? Can you hear me well? Because from what I'm looking at the screen, this looks not great. Okay, I will assume that everything is okay, but please write into the chat whether we're good. So, let's talk precision. That's very important for our FFT. Okay, now I'm a little bit scared. Let me check that everything works indeed. Yeah, I think we're okay. Yeah, I think we're okay. Sorry about that. So, as I said, we work with complex numbers. Complex numbers use doubles. We use cosine, sine. This is all precision, like error prone because of precision. Surprisingly, FFT turns out to be a very numerically stable algorithm. So even though we're doing these crazy computations, at the end we get good things. One of the reasons is that we, at the end, want to just know, we know that the answer is integral, so we can just round the answer. So if our precision, normally our precision that we want is like 10 to the minus 9 or 10 to the minus 6 relative precision. But here we care about absolute precision plus minus 0.5. If we calculate our answer with precision less than 0.5, we should be okay. So let's say that 0.3 is the safe choice, right? Here answer is different from the actual answer by 0.3. That's not a big deal. Let's quickly talk about how complex numbers work. So, not complex numbers, doubles work in C++. So we represent every number as a plus minus 1 point, like we store them in binary, of course, some number of bits after the dot, and then times 2 to some power, either positive or negative, depending on whether our number is less than 1 or more than 1. We represent every value like that. So in doubles, we have 1 bit for this plus minus. We have 52 bits for these digits after the dot, and we have 11 bits for the exponent. This is called exponent, and this is called the significand. Note that we store 52 bits, and also this bit is always 1, so we kind of have it. So we can actually store exactly any 53-bit number, plus minus. So all numbers from minus 2 to the 53 to 2 to the 53 are stored exactly. 2 to the 53 is approximately 9 times 10 to the 15. So theoretically, all numbers almost to 10 to the 16 we can store with absolute precision. But this is an upper bound, right? When we do calculation with FFT, we get more error. And in general, you can think about our FFT, right? We have some values at the top, and they're combined, and then there are log n levels of where an error can occur, right? So the final numbers are, let's say the tree of computation of the final numbers has depth log n. And this brings a lot of error. So technically, right, if we have arrays, if we do FFTs of size n, and the initial values are up to c, then the final numbers are up to nc squared, because we sum products, right? But because we have these log different levels where an error can occur, we need to take note of that. And of course, this analysis is not simple and is going to depend on your specific implementation, but we can say some words kind of in general, like different implementation. If you do a good implementation, it's going to be similar to a good implementation of some other person. And there are actual proofs for specific implementations that tell you that if you have nc squared log n at most 9 times 10 to the 14, then you're definitely safe. For specific implementation, but I guess we can have, use this for our implementation because it's very similar to what that implementation does. So you can see that from absolute precision, we kind of lose a factor of 10, and we also lose a factor of log n because we have these log n levels of computation. Note that this n should come from the size of FFT that you do. So it's probably going to be twice the size of the initial arrays, or even 4 times, because like if you had arrays of size n and m, the final is n plus m. And then we also need to double the size at most to get a power of 2. Actually, I'm not sure. Yeah, I guess it could be up to a factor of 4 larger, but whatever. This is n is the thing that we do FFT with. And this log n, I guess, is going to be 20. So we can simplify this formula to something like nc squared should be at most 4.5 times 10 to the 13. In practice, it's larger. Like in practice, people say that this number can be replaced by something like 10 to the 16. But I'm not sure. You should be careful when you go into that territory, right? So for example, we can look at some specific values of n and what values of c we get. Like for example, if we have 2 to the 17, which is like a bit more than 10 to the 5, You can use C, which is also 10 to the 5. No, this doesn't work. Doesn't make sense. What? No, I'm looking at the wrong table. We can use values that are at most 2 times 10 to the 4, so 20,000. If we get to something like 2.5 times 10 to the 5, these are going to be like 13,000. If we're getting into 5 times 10 to the 5 territory, this is going to be 9,000. If we're talking 10 to the 6, this is already 6,500. So you can see that these values C that our initial array can have are pretty small. Like, of course, it makes sense that in the end we have these huge values, n times c squared, so C cannot be large, but it's kind of improbable that we're going to have such small values in our arrays. And that's kind of the reason why a lot of the time you probably need to calculate FFT modulo some number, or you should probably use long doubles if that's not the case, right? If we're using long doubles are implementation dependent, but on modern computers, they have 63 bits of significant, so we can represent values from -2 to the 64 to 2 to the 64 inside a long double. Precisely. So actually that's an interesting thing, that long double can store more integers than long, right? Long goes from -2 to the 63 to 2 to the 63, and we can do twice as much. And we're going to have approximately the same relation, but this number is just going to grow, right? Here it was 2 to the 53, and now we have 2 to the 64, so it's going to grow by a factor of around 2 to the 11, so like 2,000. So basically we are okay if nc squared log n is at most 10 to the 18. Or in other words, if we know that this is like 20, nc squared is at most 5 times 10 to the 16. And then for these values, we get some better long doubles C. We get some better bounds. Like for example, here we're going to be okay with 7 times 10 to the 5 even. Here like 4 times 10 to the 5, 3 times 10 to the 5, and 2 times 10 to the 5. That's not bad, I think, right? So yeah, but of course long doubles are going to take even more space. And I just talked about it briefly. There's a lot more about this that you can find on the internet. All the links are in the description. But as I said, probably you're going to have to compute your FFT modulo some prime number. And there's a relatively simple way to do that. Just think about, you need to multiply two numbers, modulo 10 to the 18. But you don't have integer int 128. You have to do it inside longs. How would you do that? Let's just consider t to be square root of mod, round it down. And then we can express all the values as just like a is equal to a1 plus a2t, and b is equal to b1 plus b2t, where a1 is just a mod t and a2 is a over t. Because this is square root of mod, all these values are at most square root of mod. So now all these values are small. And now we can multiply a and b using this formula, right? a1 plus a2t times b1 plus b2t is going to be what? a1 b1 plus a1 b2 plus a2 b1t plus a2 b2 t squared. And if we compute it like multiply, take mod, multiply, take mod, all the values that you see here are at most like square root of mod. So if you multiply them, you're going to have at most mod values. So you still live inside this 10 to the 18. And we can do exactly the same thing, right? In our case, modulo is actually just 10 to the 9, approximately. But we can do the same thing. We take t equals to square root of mod, and we just break our polynomial into two polynomials. Not by degrees, but each coefficient, right? Each coefficient, we can take the less significant part of the coefficient and the more significant part of the coefficient. And then we can use the same formula, right? We have polynomials p1 and q, right? And then to calculate r, we just need to use the same formula, right? So it's p1 q1 plus p1 q2 plus q1 p2 t plus p2 q2 t squared. So we take this product of two polynomials, we add this product plus this product, and then multiply all the coefficients by t, and then we take the product of these two polynomials and multiply all the coefficients by t squared. And this will be the answer. You can see that probably we need a bunch of different FFTs here, right? We need to calculate the FFT of P1, of P2, of Q1, of Q2. Given those, we can calculate this product, this product, this product, this product. I mean, we can sum these two things up. And then we need to do 3 inverse FFTs, right? We need to inverse this, this, and this. So in total, it's going to be 7 calls to FFT. That's kind of too much. And this is exactly the situation where you can use those tricks that I told you before that we didn't cover, but you can learn about them, where you can actually do 2 FFTs inside one, or you can do 1 FFT inside a smaller FFT of size half, and then you would be able to reduce it to 3.5 FFTs, which is not that bad, but still, I mean, that's okay already, right? But even then, you can see that if our mod is like 10 to the 9 normally, right? Then our t is square root of mod, and this is the limit of our values that we have in our array. So we have an array of size n, right? If you remember what we talked about before about precision, we need nc squared log n to be at most 9 times 10 to the 14. C squared is mod, right? So we have n log n times 10 to the 9 is at most 9 times 10 to the 4. So n log n should be at most 9 times 10 to the 14, 9 times 10 to the 5. This is okay for n at most 50,000. This is very bad, obviously, right? 50,000 is not such a large array. Probably we need multiply larger arrays modulo. So most of the time, when you are doing multiplication modulo, you probably need to use long doubles. And this is going to make your code even slower. And because you have a bunch of FFTs, this is like good that we can multiply any polynomials modulo anything, but this is going to be probably slow. And this is exactly why, as I said before, people do all these much faster implementations of FFTs. So this actually works not that long. But most of the time, we actually don't have a random modulo, but we have a specific modulo. And if we have some specific modulos that are good in some way, then we can do faster, like we can do fast algorithms much simpler, let's say that. But remember that if you do long doubles, you need to change everything here to doubles, to long doubles, right? So this should be long double. And for example, when we calculate this, this should probably be a long cos and long double cos and long double sin, like cos L, sin L. And then where here it's going to be around L again. And pi, also important, this pi is not going to be precise enough. So we have to have long double and also add L here. Good. So we know how to multiply polynomials any modulo, but actually this is not how it's normally done. Normally we do something that is called a number theoretic transform, or NTT for short, which is FFT but modulo. Okay, I'm told that cosine and sine are okay with long doubles. For some reason, when I Googled it, it told me that there is a specific function for long doubles and normal works with doubles, but I believe that that's true. But I'm pretty sure that this is very important, because pi indeed is not calculated precisely enough. And this is also, of course, very important. If your values go outside of the range of doubles, like what is it, to the 53 or whatever, right, to the 53, then this is also very important. But yeah, probably with cosine and sine, we're okay. So why did we actually invent these complex numbers? Why do we need them? Because we need to solve equations of the form x to the n is equal to 1, right? We need n solutions to this equation. And because it's not possible to find n solutions to this equation in real numbers, we went to complex numbers. Yeah, you can use numbers pi also, that is already implemented in STL. Thank you. But not only inside complex numbers this equation is solvable. Like for example, so basically what we need is some value omega such that omega to the power of n is 1, but to any smaller power m smaller than n, it's not equal to 1. So we have this rotation 1, omega, omega squared, and so on, omega to the power of n minus 1. And then if we again multiply by omega, they round around. I'm not going to talk about specific like algebraic terms that you can think about it in terms. If you know them, you know them, but that's not that important for us here. I just want to tell you that there are different situations when these equations are possible to solve. For example, if we look at numbers modulo 5, right, mod 5, and we look at 2 squared. 2 squared is actually equal to minus 1 modulo 5. So actually the equation x squared is equal to 1, is equal to minus 1, right, is solvable mod 5. It's 2 and minus 2. So in some way this number 2 is like number I, but mod 5. And actually it turns out that if you have a prime number p, then equations of the form x to the n is equal to 1, mod p, are solvable sometimes, at least, depending on like for large n or whatever, not necessarily, but for specific n, yes. And precisely, if you remember how we work with numbers modulo, you can remember that when we want to take an inverse of a number, what do? We do binary exponentiation and take it to the power x to the p minus 2. Why is this the case? Why are these numbers the same mod p? Well, because if you take x that is not equal to 0, then x to the power of p minus 1 is always equal to 1, right? That's kind of what we wanted, right? We wanted some numbers to some power to be equal to 1. But sometimes in a smaller power, x is also equal to 1. Like for example, if x is equal to 1, then in every power is 1. If x is minus 1, then in every second power is 1. So not all numbers will give you this. But for a number, like we know that all numbers to some power are gonna give you 1. And then we can define the smallest such power. So it's called the order of an element. Order of x is the smallest power t, such that x to the t is equal to 1 mod p. When I write p here, it means mod p for short. We can note some simple facts about this order. First of all, it's easy to prove that order of x divides p minus 1. Why is it the case? Well, let's say that this number is t, right? And we know that x to the t is 1. Well, if x to the t is 1, then x to the 2t is also 1, x to the 3t is also 1, and so on. So we know that 0th power, t power, 2t power, and so on, all these give x to these powers is equal to 1. And we also know that, okay, p minus 1 is not divisible by t, so it's somewhere here, p minus 1, and we know that x to the p minus 1 is also 1. And x to 3t is also 1. But then this is 1 and this is 1, we can just divide. So x to the power of p minus 1 minus 3t is also 1. But you can see that this distance is t, so this distance is strictly smaller than t. So actually this number is strictly smaller than t. We just took the number p minus 1 mod t. So we got something smaller than t. And in this power we also get 1, which is a contradiction because we defined t to be the smallest power such that we get 1. So actually it turns out that all powers where x to the n, like x to some power s is equal to 1, all such powers are just multiples of the number t. So actually if we have this order, then we have like x to the 0, x to the 1, x to the 2, and so on, x to the order of x minus 1, and then we round again here. And all these numbers in between are different, obviously. It's not easy to see. It's not hard to see. And then we get kind of the same situation as we had before, right? You see here, we have some powers that round around. So we need this order, we need to find some x such that its order is equal to this power of n, is equal to n, so this power of 2. Well, we know that p minus 1 is divisible by order. So for this to be true, we need n to be a divisor of p minus 1. So actually not always this is possible. This is only possible if the number p minus 1 divides our n. But what is n? N is just some large power of 2. So we need a prime number such that p minus 1 is divisible by a large power of 2. So we need a prime number that looks something like this. 2 to the k times something else plus 1. And if you have prime numbers that look like this, where 2 to the k is larger than the values of n that you would ever need, then we're good. I mean, okay, I didn't prove that we're good, I just proved that otherwise we're not good. So now let's understand why this actually works. And this is kind of like important to remember, that we have to have primes of this form. This is actually the reason why the number 998,244,353 exists, because it's equal to y19 times 2 to the 23 plus 1. So this was always like the prime number for FFT. And like back in the days, like 10 years ago, 8 years ago, it was kind of annoying that when you see this prime number in a problem, you know that it's probably a problem on FFT. And normally people used 10 to the 9 plus 7 or 10 to the 9 plus 9. And these numbers are not of this form, so you can't use them for FFT, for entity. And then back in the days, like, yeah, if you see this modulo, probably it's a problem on FFT. And people had different opinions on what to do with that. And actually, one of the ideas was to just always use 10 to the 9 plus 7. And then we know that we can use FFT to calculate product any modular. But the problem with that is that, as I said, you probably need a very optimized version of FFT for that to work fast. NTT is going to work fast already. Like how we implemented it with complex numbers, we're just going to replace it with numbers modular, everything's going to fly. And kind of because of that reason, people just decided that, yeah, probably it's not a great idea if you need very optimized implementations of FFT to solve problems. So people decided to just stick with this number, but so that you don't know that a problem is on FFT, people just slowly stopped using these modulus. And nowadays, like on many platforms like Codeforces, most of the time when you actually need to calculate anything modular some prime number, this is going to be the prime number, even if this problem is not about FFT, but now you still don't know which problem is on FFT and which is not. There are a bunch of more of these modulus, like for example 5 times 2 to the 25 plus 1 is prime, or 7 times 2 to the 26 plus 1 is prime, and the larger is this power, the larger the arrays that you can use for FFT. But normally this is the size, because larger than 2 to the 23, that's going to be like 10 to the 7. That's already probably too much most of the time. Okay, so as I said, we need something like this, right? So every number cycles around with a period order of this number. And we need to find a number whose order is 2 to the k. So in this case, like the largest possible value, the possible power of 2 that divides p minus 1, right? So let's say that n is, let's say that it's big N. N is a power of 2, which is the largest one that divides p minus 1. An interesting fact about prime numbers is that for every prime number, there exists something that is called a primitive root. What does it mean? It means that all values except for 0, so all values from 1 to p minus 1, can be expressed as a power of g. So if I take g to the 0, g to the 1, g to the 2, and so on, g to the p minus 2, they're all going to be distinct. And because they're distinct, and there are p minus 1 values in total, they're going to be all the values. But of course, g to the p minus 1, all numbers to the power of p minus 1 are 1, so it's going to cycle. So in other words, this primitive root is a number such that its order is p minus 1, right? Before, we talked about the fact that all orders are divisors of p minus 1. So this is the largest possible order you can get, and actually this is always achievable for all prime numbers. We're not going to discuss why this is true. That's not that hard to prove, I guess, but you need to go into some algebra. We're just going to use it, right? And this is very, very similar to what we were talking about with complex numbers, right? Because now you can see that all these numbers are numbers from 1 to p minus 1. So actually, if you multiply two numbers a and b, they can be expressed as g to the x and g to the y, and then their product is g to the x plus y. So actually, in terms of multiplication, numbers from 1 to p minus 1 look very similar to this cyclic order that we had with our roots of unity, right? We took the smallest root of unity, omega, and then all the other ones were just powers of it, and then we rounded it around. And then we have the same thing here. And if you think about roots of unity, you know that the smaller roots of unity, like these are the roots of unity of power 2 to the k, like for example, right? But the roots of unity of power 2 to the k minus 1, we can also get them from here. We can just take every second one, right? For example, let's look at a picture and let's draw roots of power 12. We're going to draw 12 roots. 4 is a divisor of 12. So roots of power 4 are a part of this, right? So this is omega. We can just take omega to the 3, omega to the 6, omega to the 9, and omega to the 0. And this is going to give us roots of the fourth power. So we have g to the pi minus 1 is equal to 1. This is the solution. Like g is basically the pi minus first root of 1. And we need roots of the nth power, right? Where n is a power of 2 that divides p minus 1. This is pretty easy, right? We just take g to the power of p minus 1 over 2 to the k. And then if we take it to the power 2 to the k, we get, g to the p minus 1, so we get 1, right? So, like g to the power of p minus 1 is 1, and then we take its 2 to the kth root. This is exactly what we wanted, right? We wanted to take the nth root of this number. So actually, if we know if there exists a primitive root, then you can just take this primitive root to the power of p minus 1 over n, and then you just take out of the cyclic order, you just take less elements on this cycle, right? So we take this number times 2, this number times 3, and so on, this number times n minus 1. And then when you take it to the times n, it's going to be g to the power of p minus 1, which is just going to be 1, and then you're going to cycle again. So actually, this number always exists that we wanted. There always exists a number such that x to the power of n is equal to 1, but x to the power of n half is not equal to 1, where n is the largest power of 2 that divides p. Now we just need to find it. If we find it, we can do all the same computations we did with complex numbers, but now we're going to do the modulo. Well, how to find it, right? Actually, there are a bunch of such solutions, right? If we have a polynomial x to the n is equal to 1, we actually have n solutions to this. We are only not interested in the ones out of those that satisfy x to the n half is equal to 1, right? Wait, actually, I didn't explain that, right? Why n half? Well, because we know that x to the n is equal to 1, right? So we know that order of x is a divisor of n, so a divisor of 2 to the k. So order of x is also some power of 2. And if order of x to the power of 2 to the l is a power of is 1, so to all larger powers it's also 1. So actually, if this number doesn't work for us, it means that x to some smaller power of 2 is 1, and then also x to the n half, which is also the previous power of 2, is going to be 1. And we don't need that. So we want a number such that to the nth power it's 1, but to all smaller powers it's not 1. But actually, we don't need to check all smaller powers. We only need to check power over 2. So how many of such x's there exist, right? There are n solutions to this, and there are n half solutions to this. So we can subtract. So there are actually n half solutions to this equation. So if our power of 2 is large enough, but because we're trying to do FFT mod that, this number is going to be probably like 10 to the 5, 10 to the 6, right? In our case, it's 2 to the 23. So we have 2 to the 22 solutions to this equation. So if we pick a random value, then we're going to succeed with probability mod over 2 to the 22. And then we just binary exponentiate this value to the power of n, check that it's 1. Binary exponentiate it to the power of n half, check that it's not 1. And if that's the case, then we're golden. So there are this number, wait, this is not the probability, right? The probability is 2 to the 22 over mod. But this is a very large number. Like, this is 10 to the 6, this is 10 to the 9, so this is like 1 over 1,000. So if we need to check like 1,000 numbers approximately to find the right one. But actually, you don't even need to check random ones. It turns out that you can actually go from 1, 2, 3, 4, 5 and check sequentially. And as it turns out, your roots are kind of randomly distributed People don't know how to prove it, but if I remember correctly, this is like, if the Riemann's hypothesis is true, then it's true that you need to check only like a polylogarithmic factor. No. What I'm talking about is for primitive root. For this thing, actually, I have no idea. Yeah, but it's just heuristic note that for all the prime numbers that we have, if you just check sequentially, you're going to find it quickly. But because our prime number is fixed, you can do it once, right? So you don't need to do it every time when you run your code. You just do it once. Even if it takes a long time, you can just hard code it into your solution. But for example, for our mode 998244353, this primitive root of power 2 to the 23, right? Was it 2 to the 23? I forgot. 2 to the 23, yes. This is actually 31, so this is a very small number, and we quickly can find it. And now we just replace our W with this thing and calculate everything modulo, and everything's going to work like magic, because we didn't really use the fact that we use complex numbers, just some numbers such that there exists a value such that omega squared, omega to n minus 1, n minus 2 are distinct, and then they wrap around. Okay, the smallest primitive, oh yeah, okay, it's proven to be log to the 5, but it's conditioned on like Riemann's hypothesis that it's like log to the 3 or something like that, if I remember correctly. Because log to the 5 is a pretty large number, I guess. I mean, it's okay, but yeah. Anyway, but basically this is not important for us. For us, what's important is for modules that are gonna occur for you, if you just go through numbers 1, 2, 3, 4, 5, very quickly, basically in 0 time, you're gonna find the root. So you don't need to pre-compute it. You can compute it inside your code. That's not a problem. Great, let's write our code. So we do everything the same way. We just replace everything from complex numbers to integers modulo, right? So we don't have this pi anymore. We have our modulo 998244353, and we have the largest power of 2 that goes into mod minus 1, and we have our root, right? Our root, remember, we don't use the primitive root, but instead we use the root of power 2 to the 23, or whatever, the largest power of 2. You can also store the primitive root. Yeah, that's not that important. We're going to store this thing. So we need to implement some operations modulo, right? A, B, let's multiply them. This is like A times B in longs. Addition of A and B is like A plus B at least mod. Then it's A plus B minus mod, otherwise it's A plus B. The same for subtraction. If A minus B is less than 0, then we go A minus B plus mod, otherwise A minus B. Binary power I haven't implemented, so I'm not gonna write it down myself. Good, now we have these values W that we need to compute. They're gonna be integers. Here we need to compute the first primitive root, right? Actually, now there is no problem with multiplying, right? Because multiplying a bunch of times, we still work in integers, so there's no precision errors. But still, if you're gonna do it here inside FFT, you're gonna have like additional n log n multiplications modulo, which you need to take mod, so that's kind of long. So it still kind of makes sense to pre-compute these. So our first W is going to be the primitive root of the power n, right? We have a primitive root of the power pov2. So as I said, we need to take it, this root, to a power of pov2 over n, right? So if we would take it to the power of pov2, this would be the first time it hits 1, but we multiply it over n, so this is a root of the nth power. And this all stays the same. There's nothing different here. Well, what happens here? I don't think anything happens here. Okay, the difference is here, right? We need to divide by n, but we need to divide modulo. So we'll have inverse n, which is n to the power of mod minus 2. And we're going to multiply here by this inverse n. And yeah, I guess I forgot that all these should be also done modulo. So this is like add, multiply, and this is subtract, multiply. And then in our multiplication, now actually we don't need long-longs because we're computing everything modulo. Oh, okay, this is our complex multiplication. Let's bring back the real normal multiplication, right? So we're gonna resize actually the array P to be n, because we don't need our different array that is complex because we work with integers. We're gonna resize Q, then we can just multiply all the values again modulo, and then we take P back, and I guess we can just return P now, right? We don't need to round anything. Everything became much smaller, but the most important part is that there are two improvements, right? First of all, we kind of decreased our memory by a factor of 4, or even more than that. This should be resized, right? Because we created vectors of complex numbers. Complex number is a pair of doubles. Double is a 64-bit number. And now instead of two 64 numbers, we store one integer. That's pretty nice. And now when we multiply modulo, we only do, wait, I didn't do FFT. Let's do FFT of P and Q, yeah. Now we only have 3 FFTs, normal amount. And before, when we multiplied modulo, we had like 7. And if you need some more like improvements to actually make it like 3.5 or something like that. But the caveat is that if we just multiply two things, now we have to have 3 FFTs. We cannot use that trick with where we put P and Q into real and imaginary parts and multiply them somehow, blah, blah, blah. Great. I guess the last part that I didn't talk about is finding the root, right? Let's find the root. So void find root. We first find the largest power that goes into our modulo. So while modulo minus 1 is divisible by the next power of 2, I increase it I multiply by 2, and now I just find my root. I find my root just by a brute force search. So I check so my number should be into the power n, which is pof2 in this case, right? To the power of pof2 should be 1, but to the power of pof2 over 2 should not be 1. So we check that while it's not true that either it's to the power of pof2 not 1, or to the power of pof2 over 2 is equal to 1, I need to go to the next root. And simple exercise for you is actually we can make both of these checks in only one exponentiation. So actually you can, you only kind of need this check. You can think about it. Okay, and that's everything that we had. Now we have our natural transform. Number theoretic transform. And without any further optimizations, right, we did already some optimizations for complex FFT. Some of them are actually not even needed here, right? Because, for example, this doing 2 FFTs in 1, we're not using that. But even with everything that we did here, this is already pretty fast because we're not using doubles. We are multiplying numbers modulo, but that's not such a big deal. Yeah. And this algorithm for our constraints that we had works in 0.5 seconds. So even a little bit faster than the fastest implementation of FFT that we had, right? Our fastest FFT implementation worked in 0.6 seconds, and this one works in 0.5. You can go again for much more improvements, and there is the specific website, Yosupo Judge, where people actually do these things, where they can try to make algorithms as fast as possible. You can see the links in the description to different FFTs that you can submit on that website. And on that website, if I took the fastest implementation of NTT, it actually works in 80 milliseconds on the inputs that we have. So this is another like factor 6 improvement to our algorithm. So there is a long way to go, but that's not very relevant. Like, you already can solve almost all problems that exist. Great. That is kinda all the theoretical topics that I had for you today. Again, I'm running out of time very quickly. Sorry for that. But I hope that this is informative. After that, you can watch it on 2x speed, hopefully. So we learned all the theory. That's great. Everything that's left for us to do is to learn more applications. So we're going to learn how to multiply a bunch of polynomials. We're going to solve some trickier problems, like how to do pattern matching. And actually, we're going to learn how to do pattern matching with wildcard characters, even if the size of the alphabet is large. And we want to learn how to do online version of FFT, right? As I said at the beginning, when one of the arrays arrives to you one by one. This is what we're going to do now. Ask questions if you have any. Okay. So the first problem is how to multiply a bunch of polynomials, right? We learned how to multiply two polynomials, but imagine that you have a bunch of polynomials, P1, P2, and so on, M, and their total degree is n. So the product will be of size n, but these polynomials, there are a bunch of them, up to n, right? And if you multiply one by one, it's going to be like nm log n, I guess. So the right answer, what you should do is you should multiply them in a tree structure. So you should do divide and conquer, right? You divide by 2, recursively compute the product on the left, the product on the right, and then combine them together. This is actually exactly the same thing that we did with our subset sum. In our subset sum, basically all the polynomials were of form 1 plus x to the si, right? We either take this element or not, and then we had to multiply all these polynomials. So the total time complexity is going to be n log m. But there is a very nice, like, constant optimization of this algorithm. A constant optimization of this algorithm tells us to take an STD set and store pairs of the form degree of polynomial pi and index of pi, so basically I, we store I, in a set. And always take two smallest degree polynomials out of the set, multiply them, and then put it back into your set. This is not going to improve your algorithm asymptotically. It's going to be still n log m, but it could bring you a better log factor. For example, in this situation where you have a small number of large polynomials and a very large number of very small polynomials, right? Then most of the time you're going to be working with these small polynomials, and only when they grow to the sizes of these larger, then they are going to be involved. And this is basically the same thing as Huffman codes, if you heard of this thing, right? When we're trying to encode a bunch of words using binary strings so that no code word is a prefix of another, we also construct some tree, and we always take the two least, the two words that appear the least number of times, and we kind of combine them together into one word, and then we continue. And we get this tree structure. Here we also get a tree structure, right? The same way as with this recursive divide and conquer algorithm. We take two polynomials and we combine them, then we combine this with some other polynomial and so on. And this is a nice exercise to see that the depth of this tree is still going to be of log n. Log m, right? M, yes, m. So this is why this algorithm also works in of n log n log m time, but with probably a nicer constant factor. Cool. The second problem that we're going to talk about is pattern matching, which is kind of surprising, right? Because pattern matching is a string problem and we have string algorithms, and this is FFT, this is polynomials. But FFT is also an algorithm that works on sequences of numbers. But we can reinterpret characters as numbers and then do FFT on strings. And maybe we're going to get something interesting from that. So imagine that we want to do pattern matching on strings of binary strings. So we have strings, this is like a text T, and we have a pattern P, and we want to find where this pattern occurs. The normal solution is to write these two strings together and then run either Knut-Morris-Pratt algorithm, so prefix function, or Z function, something like that, in linear time. But we are crazy people. We're going to solve this problem using FFT. So let's reinterpret this problem a little bit, right? Let's look at the string T. And for every position, k, let's see if we put the pattern P here, how many matches there are going to be. And we're going to count these matches separately. We're going to count matches 1 to 1 in one go, and then we're going to count matches 0 to 0. So what does the number of matches of 1 to 1 mean? It's a sum over all indices of P, like from j equals 0 to size of P minus 1. We need to count the number of positions such that S, okay, not S, it's easier S. Let's call the string S. Such that S, what is it? K plus J is equal to 1 and P J is equal to 1. So we want to count how many positions satisfy this constraint. But if these values are zeros and ones, then this is the same as just multiply these two characters, right? If any of them is 0, the result is going to be 0, so we're not going to add anything to the answer. But if both of them are 1, we're going to add 1 to the answer. So this way, if we just run FFT, kind of FFT, right? This is not exactly FFT, because in FFT, so this is like answer k, right? In FFT, the sum of these indices should be k, and in this case, the difference of indices is k. Almost the same thing. But if we run this weird FFT, then we're going to get exactly for every index how many ones match with ones. And then we can just reverse all the values, right? We can switch zeros and ones and run this thing again, and we're going to get ans prime k, which is going to be the number of zeros that match zeros. And if we add them up, and if this value is equal to the length of the pattern, it means that every character matches. So for every character, it's either 0, 0 or 1, 1. The only problem is we need to compute this weird convolution. So where answer k is equal to the sum of k plus j times pj. So instead of all pairs that sum up to k, we take all pairs where their difference is k. This is very simple to do. Let's just reverse the array P, right? If we reverse the array P, then index j is going to become like n minus j minus 1. And then their sum is n plus k minus 1. So if we reverse the second string and convolve them, then answer k is going to be stored in the convolution at index n plus k minus 1. So if we reverse the string p, now instead of subtracting two indices, we can add two indices. That's simple. Okay, so we can solve this problem with two polynomial multiplication in n log n time. This is probably worse than Knut-Morris-Pratt or whatever, because that's a linear time algorithm. But actually, I'm not sure about that. I didn't investigate that because, as I told you, we have very, very efficient implementations of FFT. And those implementations of FFT, they work even faster than reading the input from the input file. And our string algorithms, I think they're not very cache efficient, right? Because they jump all the time between weird indices. So I think that if you take the best implementation of FFT, this could even be faster for binary alphabets. But of course we want to do more, right? Actually, our algorithm does even more than that, right? For every position, it counts how many things match, right? String algorithms normally only tell you, does it match or not? So does it match completely or not? And here we can learn how much it matches, right? And we can make this algorithm more general. Like we can introduce question marks into our pattern P, right? And a question mark means that this character matches anything, and then this is not a problem, right? So first of all, we put all the ones, we take all the ones, and we consider everything that matches ones. So we multiplied before S and T, but now we're just going to replace question marks with ones. So question marks also match. Now we're talking about pattern matching in strings with wildcards using FFT. So we replace all question marks also with ones, and then we multiply, and then we get how many ones from the string X, from the string S match. And then we can do the same thing with zeros, right? We get zeros, we put ones on the positions where we have zeros or question marks, right? And then we multiply, and then we get whether a pattern matches S and T. And then we can do that even if S also contains, this is not S and T, this is S and P. If S also contains question marks, again, question mark can be any symbol. So for both 1 and 0, we set it to be equal to 1. The only problem is that question marks can match question marks, and then we're going to count it twice, both as 0 matching 0 and 1 matching 1. So if you have question marks both is in S and P, you're going to need 3 FFTs, right? You're going to need to do some kind of inclusion-exclusion formula. You count the possible number of zeros that match, the possible number of ones that match, and then subtract question marks that match each other because you counted those twice. Yes, I counted matching zeros into account. I guess I didn't draw it. So answer K gave us the number of matching ones. Answer prime K gave us the number of matching zeros. We just flipped the strings, right? We replaced all the zeros with ones, all the ones with zeros, multiplied. But here we need 3 FFTs, right? If you have a larger alphabet, you need to do this thing for every single character. So this is going to work in time sigma times n log n, where sigma is the size of the alphabet. But actually you can do better. You can just imagine your characters to be encoded in binary alphabet. So all your characters are just encoded in binary alphabet of size log sigma. And then we can just match that all bits in these binary representation match. So first you create strings, binary strings, where you put the least significant bit of every character. And then you check that it matches. Then instead of least significant bit, you put the next significant bit, and so on. So we're going to do log sigma different pattern matchings on strings of 0, 1s, and this is going to work in time n times log n log sigma, which is better than sigma here. And if a string matches, then it means that for every character, every bit of this character should match every bit of this character. And if it doesn't match, then there exists a bit where they're not going to match. So this is a valid way to do this. But note that this way we're not going to find, so before we found for every position where we put p, how many characters match. And here we're only going to learn whether it matches or not. And as an exercise, you can think how we can use square root decomposition to solve this problem in time n square root of n log n. So if I have two strings of large alphabet, size n alphabet, and I want for every position of the largest string, check if I put the pattern here, how many characters are going to match. This is a very simple heavy, light square root decomposition. Okay, but actually you can solve this problem when you have, so if I only care about the exact match, right, I can solve this problem in just a single polynomial multiplication. And this is a great idea that you can think about, that you can think about a more general convolution, right? Our convolution is just very restricted, right? You have sum of p k times q j minus k, and this is answer j. But you can encode a bunch of more algebraic things here, right? So if we go back, right, we want to match at position k whether string s and p match. So what does it mean? We want to sum up over all positions. Is it true that sk plus j over oj is equal to pj? And we want to check that for all j they are equal, right? I cannot do this. This is not an algebraic thing, so I cannot do this with FFT. But I can do some kind of functions of sk plus j and pj. Again, this is not a convolution, but you reverse p and then it becomes a convolution. What kind of functions f I can do? Like, obviously I can do this function, sk plus j times pj, right? Product we can do. But I can do something different, right? I can square s. I can take sk plus j squared times pj. For that, I just, in the initial sequence s, I just square all the elements and then I convolve it with p. And this way I'm going to get this value, right? So this is ans k. Now we're going to change our strategy. So before, we're trying ans k to be equal to the size of p when they match. But this time we're going to do the opposite thing. We want some function f such that it's 0 if match and otherwise non-zero if they don't match. So basically we're going to count the number of mismatches. And if at the end this ans k is equal to 0, then it would mean that they match, and otherwise it means that they don't match. So we need some kind of function fab that is somehow algebraic, right? And it should be 0 if we have a match and non-zero if it's not a match. Well, that's obvious. You can just take a minus b. But that's not going to work for us, right? Because this value can sometimes be negative. And then if we sum some things up, we have a summation sign here. If we sum some negative, positive values, at the end we can get 0. But we don't want to get 0 if we only want to get 0 at the end if all the summands are zeros. So we want this value to be not just non-zero, but strictly positive if they don't match. This is also not hard, right? You just take a minus b squared. And this is good, right? This should be enough for us. If a and b match, this is 0. Otherwise, it's positive. So if there is a single mismatch, Like, we just think about our characters as numbers between 1 and n, right? There is a single mismatch, the sum is going to be positive, and if all of them match, it's going to be 0, right? So how do we calculate that? We need answer k to be equal to sum over all indices j, sk plus j minus pj squared. But we should just open the brackets here. So what is this equal to? This is sk plus j squared plus pj squared minus 2 sk plus j pj. Actually, this is only depends on s, so this is simple to add to the answer. It's just sum of squares of s on this segment. So we just square all the values on s and take a sum on the segment. Again, we take all squares of all the values on p, and then we just subtract, right? In total, this is sum over j, 2 times sum over j, sk plus j times pj. And this is where we have a convolution. Only here, we need to do a convolution. And then if we take like sum on a segment plus of squares, sum of all squares in p, and then subtract twice the convolution, blah, 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 we get ans k. And we know that ans k is 0 if and only if they match. Again, this is not very interesting because we have z function and prefix function that can do these things. So the only interesting situation is if we have wildcards. So if we have question marks in strings p and s. But I want to say that implementing those is not that hard. So we want this function f to be 0 not only if they match, but if a is equal to question mark or b is equal to question mark. So if one of these 3 conditions happens. But this is also not hard to do. I'm just going to think about question mark as a value 0, so all my characters are values 1, 2, 3, 4, 5, and so on, and question mark is 0. And then I'm going to take a minus b squared times a times b. And then if either a or b is 0, this is also going to be 0. So this value is always non-negative, obviously, and it's 0 if one of the 3 things happens. Either the characters are the same, or a is a question mark, or b is a question mark. And now we can just do the same thing. Let's reduce this expression, right? Now we have this kind of formula. What is this expression reduced? It's going to be ck plus j cubed times pj plus pj cubed times ck plus j minus 2 ck plus j squared pj squared, right? And this is just 3 different convolutions. We take an array where we cube all the values of s and we convolve it with p. We take an array where we cube all the values of p and we convolve it with s. And when we cube the when we square the values on s and p and we convolve them together. So using just 3 matrix multiplications, we can do our pattern matching in the general case. And this is a good idea, right? Well, note that we still think about FFT as a black box. 99.9% of the time you still think about FFT as a black box. But convolutions and multiplications of vectors, of polynomials, still can express a bunch of different things. And that is a very interesting fact. That is highly non-trivial, I would say. Okay, I think that was one of the most informative problems that we had. We just have 2 more problems and we're done. So the next problem is again about thinking about things in terms of polynomials and how we can convolve multiple things at the same time. So imagine that we're given a number n and a set d of positive integers, right? And we want to count trees on n vertices such that degrees of O nodes are taken from the set of D. So for all nodes of the tree, their degrees have to be from the set big D. Obviously, number 1 should be in this set, right? Because every tree has a leaf. But other than that, it seems kind of complicated. And obviously, we're counting it modulo 998244353. So we will need two things. We will first need to know some things about, like, mathematical facts about trees, and then we're going to need to use FFT. So the first thing is, imagine that we don't have any restriction on D. So we can use any kind of degrees. So we need to count how many trees there exist on n vertices. This is a classical problem. Maybe you know this, maybe you don't, but the answer is n to the power of n minus 2. And the reason for that is that there is a bijection between trees of on vertices 1 to 3 and so on n, and arrays of size n minus 2, where every element is a vertex of that tree. So every element is a number from 1 to n. How many arrays of length n minus 2 there are? Every element has n choices, so there are n to the power of n minus 2 such arrays. This is called Prüfer's codes, how to encode a tree. And actually, if you look at how these codes work, it's very simple actually, a very simple process of encoding. Every vertex v appears in the sequence exactly the degree of v minus 1 times, right? So the sum of all degrees is what? It's 2n minus 2, right? So the sum of degrees minus 1 is exactly n minus 2. So that's why the length of this vector is n minus 2. And how many? So we know, imagine that we fix degrees, right? We fix degrees. So the vertex 1 has degree, I don't know, deg 1. The vertex 2 has degree deg 2, and so on. Weird. Let's call them E1, E2, and so on, En, right? So the number 1 should appear in this sequence E1 times, E1 minus 1 times. The number 2 should appear E2 minus 1 times, and so on. How many such vectors there exist? Well, this is the definition of a multinomial coefficient, right? Basically, you need to take, like, write them in a sorted order. Then there are n minus 2 factorial options of how we can permute them. But then we count it multiple times, right? Because we have E1 minus 1 elements that are equal to 1. We can permute them however we want, and this will not change anything. And the same way with these, and so on. So this is n minus 2 factorial over E1 minus 1 factorial times E2 minus 1 factorial, and so on, En minus 1 factorial. This is the answer. And this is the multinomial coefficient, n minus 2 over E1 minus 1, E2 minus 1, and so on, En minus 1. And what we are interested in, right? This is for fixed degrees, but our degrees are not fixed. We want to sum up over all values like D1, D2, and so on, Dn from the set D, these values, right? So if all degrees are from our set, we want to calculate this sum. When we have some crazy algebraic formula, we should break it down. So first of all, we take this out of the sum. It's just n minus 2 factorial outside. And here's just 1 over. And let's call these things. Let's define ai to be equal to 1 over di minus 1 factorial, right? Oh, wait, it's not this, right? they should be taken from D, but also the sum of the degrees should be 2n minus 2, right? So that this equation makes sense. And if we define such a thing, right, this makes sense because we work modulo, right? So we're interested in sum over all indices, like using indices such that d1 plus d2 plus so on plus dn is equal to, wait, what did I do? No, that's not what I wanted. That's not what I wanted. I wanted to define AD to be equal to 1 over d minus 1 factorial. And then we're summing up over all such things such that they sum up to 2n minus 2. And they are from the set of the values AD1 times AD2 and so on times ADN. This is what we want. And then there is n minus 2 factorial at the beginning. Note that this is very similar to a convolution. If n would be equal to 2, we would have only 2 factors here, and we go over all pairs d1, d2 such that they sum up to something specific. And here, we just have an n-wise convolution. So actually we need to convolute all of them one by one, right? And what do we convolve? We convolve these things, allowed set D. So we can just create some kind of vector of size n from 0 to n, and we're going to mark all the degrees that are allowed. This is going to be a polynomial p, and what we're interested in, we want to take p to the nth power and take its coefficient, like this is going to be r. We want to take r to n minus second coefficient, right? Because if you think about it, we can write p as a sum of some degrees, right? To also here degree. And if you multiply, like you write down all the summands, if you multiply all these brackets, you're going to take some power from every bracket, and these powers should sum up to 2n minus 2, exactly. And then we're going to multiply a of this power, a of this power, and so on. So this is exactly what we wanted. So what we're interested in is we take this polynomial of size n, we take it to the nth power, and we take its 2n minus second coefficient. Well, that's not that hard to do. Like you can't do it stupidly because p to the n has power n squared, right? But we don't care about large powers. We only care about powers up to 2n minus 2. Larger powers do not influence us anymore. So we're just going to run binary exponentiation on this. And every time we multiply, we're just going to cut only 2n minus 2 powers. And then it's going to be n log squared n time to calculate the answer, right? Note that you could think about a different solution, right? Because what does FFT does? We take a polynomial p, we go into its value representation, right? x1 and so on, p of x n minus 1. And then if we have value representation, it's easy to power our polynomial. We can just binary exponentiate all these values, and then we can try to go back. The problem is that this only works if the number of samples is as large, like larger than the degree of the resulting polynomial. But if we exponentiate a polynomial, its degree grows very rapidly, right? So we would need n squared samples to be able to go back. So this wouldn't work if you would just say take, I don't know, FFT of size 2n, apply it, exponentiate all the values, and then go back. Because actually you would get like a polynomial of degree n squared, but then all its coefficients are going to cycle through, and then in the actual values you're going to get some garbage. It's going to only work if the size of my polynomial was constant. Like if my polynomial was something like x cubed plus 7x plus 4 plus 5, right? Then it's gonna work, because I need the number of points to be the degree of final polynomial. But if this degree is constant, then this degree is at most 3n. So I can evaluate this polynomial just in 3n points, exponentiate all these points, and then go back. And then it will work in O of n log time. But be careful, right? You always need to have the number of points at least the degree of the result. So this idea of exponentiating the values in the value representation is nice, but most of the time I think it doesn't work. I'm not sure. Maybe there are situations where, I mean, this is the situation where it works, right? But yeah, so a constant sized polynomial you can take to the nth power in n log n time. That's true. Okay, and finally, the last problem that we have here today is online FFT that I talked about at the beginning. I think some of you came here to hear about that specifically and had to wait for 3.5 hours. Sorry about that. So we're going to talk about a problem. You can find this problem in the description. It's called Counting Road Networks from HackerRank. This is a very simple problem. I just want to find so before, in the previous problem, we counted the number of trees where we have some limitations of the number of among the degrees. Here, I just want to count the number of connected graphs on n vertices. Online FFT. These are very confusing names, like in different places they're used for different things. Sometimes this is also called relaxed convolution, but I honestly don't really know which term represents what. I just use them, I just say online FFT for everything possible. So I want to count number of connected graphs on n vertices. How am I gonna do that? Let's think. Well, it's pretty simple to count the total number of graphs on n vertices, right? Because we have n times n minus 1 over half edges potential, and for every edge I can either take it or not. So there are 2 to the power of n times n minus 1 over 2 graphs in total. Let's call this O of n. 2 to the power of n times n minus 1 over 2. And what I am interested is, so connected, right? Connected of n is basically O of n minus disconnected of n. That's what we're going to compute. So how many disconnected graphs on n vertices there are? Well, let's take the first vertex. It lies in some connected component, and everything else is any kind of graph. So actually, this can be written down as O of n plus sum, what did I do? Not equal, and not plus, but minus. Sum for m from 1 to n minus 1. So m is the size of the connected component of vertex 1. It has at least vertex 1, but it can't be n because then graph would be connected. We need some number of connected graphs on m vertices, right? How many connected components of size m there are, times everything else. But everything else can be any graph. So it's O of n minus m. And this is the formula. Number of connected graphs on n vertices is number of O graphs minus disconnected, which is sum over the size of the connected component of vertex 1 of how many ways there are to create this connected component, how many ways there are to create the rest of the graph. Note that this is O, this is not connected, right? So it does not necessarily have 2 connected components, it can have more. This is very similar to convolution, right? This is m, this is n minus m. The only problem is that it relies on itself, right? It depends on itself. Wait, actually I think this formula is not correct, right? Because I not only need to create a connected component on m vertices, I first need to choose which vertices are going to be in the connected component of 1, right? There are like n minus 1 vertices except for 1, and then you choose m minus 1 out of them. So this is actually a little bit more complicated than a convolution, but if we simplify this formula, we can see that it's similar, right? So this is just n minus 1 factorial over m minus 1 factorial times n minus m factorial, right? So we can just kind of separate these things. This is going to be connected to this. This is going to be connected to, oops. This is going to be connected to this, and this we can take out. Anyway, let's simplify this formula. So I have a simplification here. Let's define P of n as connected component of n over n minus 1 factorial. And let's define Q of n as O on n over n factorial. So this is basically the probability of a graph. No, I don't know what I said. This is not a probability of anyway. And we can rewrite this formula in this way, right? We're going to divide everything by n minus 1 factorial. So here we're going to have connected over n minus 1 factorial. So it's going to be P of n is equal to O of n over n minus 1 factorial. So it's like n times Q of n minus sum over O m from 1 to n minus 1. Connected m over m minus 1 factorial is P of m times O of n minus 1 m over n minus m factorial, which is Q of n minus m. Now we indeed have a convolution. This is good. So Q we know. Q is easy. This is like 2 to the power of n times n minus 1 half over n factorial. This can be calculated. And we want to learn m. We want to learn p. If we learn p, after that we can just multiply by a factorial and get the answer, how many connected graphs there are. So we want to be able to compute some kind of this thing. We want to compute p that depends on p and q, where we know q, but p depends on itself. So it's some kind of online FFT. And in general, we can solve any kind of formula that looks like this. So we have a of n that is some, let's say, some function of n and sum over all smaller indices, right? Wait, what am I doing? So 1 to, I guess from 0, right? Here we, from 1, just because, let's say that P of 0 is 0, right? Because there are no, let's say there are no connected graph on 0 vertices. I actually had once a discussion that lasted a long time, whether an empty graph is a connected graph or not. Surprisingly, it's an unclear conversation, but let's say that we sum up from 0, and we just say that P of 0 is 0. Of the form ai times bn minus I, right? So it depends on all the previous indices of a multiplied by b, and then we can apply some function to it. In our case, this function is n times q of n minus this thing. How we're going to do that? Well, this is simple, actually, in this case. We just do divide and conquer, right? So we have this kind of formula, and every p of m that is smaller than p of n should be somehow multiplied with the corresponding coefficient and added to the right place, right? Okay, so what we're going to do, we're going to have divide and conquer. We're going to recursively solve the problem on the left half. So now everything on the left is solved. So now we have the correct values of p on the left by the induction hypothesis. And now we want to calculate the influence of the left part on the right part. I think there is some name for it, something like CDQ divide and conquer or something like that. Actually, maybe I should have included it in the materials below. If anybody knows the name, you can give the name in the chat. So there is this classical idea that to calculate something, we calculate it on the left, then we calculate the influence of the left part on the right part, and then we recurse on the right part. So what is the influence, right? So all the values pi from here, how do they influence this part? Well, we just take this and we multiply it by q, and then we learn what is the influence of the left part onto the right part. So we actually need to do only one FFT. So we run on the left, we compute it correctly the values on the left, then we run one FFT, we compute the influence and add this influence onto the right part, and then we recursively go into the right part. And our invariant is that whenever we go into any segment, all the influence of the stuff before it is already calculated. So we only need to calculate the influence inside this part. And then it just works. And it takes analog squared n time, because it's divide and conquer plus FFT on every level. This is sufficient for this problem, but I want to say that we can do it even in a more general sense, right? Because in this case, let me think how to phrase this. So let's say that we have a normal convolution this time, right? So ck is equal to sum over oj from 0 to k a j times b k minus j, right? And imagine that I'm given the values of a in advance, but values of b are given to me only one by one. And when I know b0, b1, and so on, b like l, these are the only values of b I need, theoretically, to know the value cl, right? To know all the values c0 and so on cl. So theoretically, already when I'm given all these values, I should be able to compute the prefix of c. And I want to say that it's a more general formula than what we're having here, right? Because imagine that we don't know p's in advance, right? We just get them one by one, and one by one means that we calculate this value, right? Using this formula, and when we plug it in, now we know pn, and now we can calculate the influence of this value on the rest. And this is kind of a more general situation, right? When just one of the arrays is given, and this is given to us online. And I want to say that we still should be able, during the whole time of the algorithm, we should be able to work in analog squared n time, but after every value of b is given to us, we already should be able to calculate the corresponding value of c. How to do that? Actually, it's also not that complicated. Let's take our array A, right? Our array A is given to us in advance. We're going to break it into blocks. The first block is going to be of size 1. The second is also going to be of size 1. And then they're going to be powers of 2. And so on, right? So 1, 1, 2, 4, 8, 16, and so on. So basically, the end of every, like the start of every block, except for the 0th one, is a power of 2, right? So this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, blah, 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 right? So this block starts at 1, 2, 4, 8, and so on, right? And we need to multiply, right, a by b. This is a, and this is b, which were given only one by one. And we're going to treat a as just like different blocks of a are going to be treated separately. So we're going to multiply this block of a with b. Separately, we're going to multiply this block of a with b. Separately, we're going to multiply this block of a with b. And each block we're going to multiply with a different frequency, right? For example, this block has size like 2 to the L, right? And doing a multiplication on arrays of this size takes time 2 to the L times log 2 to the L. We can't do it on every iteration, right? That's too much work. For this to make sense, we should do it approximately n over 2 to the L times, right? So that this ends up to be n times log, and we have log different blocks, and the rest and everything together adds up to be n log squared. So actually, with this value, we're going to multiply always. This is actually very simple, right? Because A0 is multiplied by bk. So as soon as we're given bk, we just add this value, bk times A0 to ck. So this is, we kind of don't consider this to be a block. This is just C0, this is just A0. And all the other blocks, we will multiply them with frequency that is equal to its length. So with this block, we're going to multiply on every single iteration, right? So as soon as we get a new element, we multiply it with this guy. As soon as we get a new element, we multiply it with this guy. A block of size 2, we're going to multiply with blocks of size 2, right? We're also, imagine that B is broken into blocks of size 2, and when a block is complete, we're going to multiply this block with these blocks. The same with 4, right? When we think about 4, we imagine that B is broken down into blocks of size 4, and when a block is complete, we multiply it by the corresponding block in A. Obviously, at the end of the algorithm, we're going to compute the convolution, right? Because every element from A is a part of exactly one block, and each block at the end is going to be multiplied with everything in B, right? Okay, I mean, I guess I assume that B has the size of power of 2, otherwise you can have some block that is not finished. So let's assume that both A and B at the end have a size of power of 2. But, so the only thing that is left is two things, right? Check time complexity, and the other one is verify that, yes, it's true, all the influences at the end are going to be computed, but I need to know that when I get to the index k, ck is already computed correctly. So why is it the case? Let's see. We know that the block of size 2 to the k starts at index 2 to the k. This is a nice coincidence, right? So this is a block of A that starts at index 2 to the k, and we multiply it with blocks of B of size 2 to the k, right? I guess k is a bad number. Let's call it L. And we have our current index k, which is maybe somewhere inside a block. So we actually haven't yet multiplied this block of B with this block of A. But I want to say that its influence only starts here. So it does not influence index k. Why is it the case? Let's look at this block, right? This block started at some position, I don't know, position j, and this is position j plus 2 to the L, right? If I multiply this by this, which indices do we have? The smallest index that we have is g plus 2 to the L, and there are some larger indices. But if I multiply this block by this block, what is the smallest index that I can have? It's g plus 2 to the... Okay, I guess this is a weird name. Let's just call this j. I don't care about the previous block, actually. So this is just index j, right? And if I multiply this block by this block, the smallest index that I have is j plus 2 to the L. So the smallest position where I get an influence is inside the next block. So even though I am inside this block k and I haven't yet multiplied by it, anyway, it's not important because the influence of multiplying these two blocks only starts in the next block. So only these multiplying this block of A with these blocks of B influences my value. And because all of them are already finished, I already multiplied it. So indeed, when I arrive at element k, I have already correctly computed it. And what is the time complexity, right? We multiply blocks of size 2 to the L. It takes time 2 to the L times log 2 to the L. And we do it every 2 to the Lth iteration. So it's n over 2 to the L, which is n log 2 to the L, which is at most n log n. And because we have logarithmic number of different blocks of A, in total, this takes the same time complexity as the previous algorithm, so just n log squared n. But this time we actually have this online behavior. How to implement it? You just get all the values of k, right? And then when you get a new value of k, you look at the next index and you see by which powers of 2 this index is divisible, which would mean that which segments start here. So this would mean which segments end here. So if k is divisible by 2, right, divisible by 1, which is always the case, we multiply it with the first block. If k is divisible by 2, we multiply the last block, like the last 2 elements here with the last 2 elements here. If k is divisible by 4, not k plus 1, right? If k plus 1 is divisible by 4, I take the next block of size 4 in A, and I multiply it by a block of 4 here, and so on. Note that, for example, when k plus 1 is a power of 2, I take a block of size k here, and the corresponding block of size, so this is a power of 2 to the L, right? We know that a block of size 2 to the L starts here, so this is to the right. And this is actually like the only situation where we use the fact that A is given to us in advance and only B is given to us online, right? So we actually use the values of A that we don't know yet. And that's the last exercise I have for you, is to think about, can we somehow split this algorithm into 2 parts or something like that, so that we can compute online FFT if both A and B are given to us online. So at iteration k, we're given AK and BK, and we need to be able to compute CK at that specific point in time. That's an interesting question to improve your understanding of how this algorithm works. Great. This is everything that I had for you today. I was hoping that it's going to be less than last time. I was hoping that it's going to be 2.5 hours. It ended up to be 4 hours. That is absolutely insane. I'm sorry for that. But I hope that this was instructive. Even for me, it was instructive. I never learned about precision of FFT before. I just knew that it's kind of okay. If it's not okay, you should replace with long doubles. But if you're doing modulo, you probably should just use number theoretic transform. But now I learned actually that there are specific bounds that we should use. Okay, this is the end of the lecture. Thanks to everybody for listening. If you have any questions, I'm happy to answer them. And otherwise, thank you very much for attending. This was a very, very long lecture, and I really, really hope that you learned something new today. I'm going to sit here for a couple more minutes, and after that, I'm going to conclude the stream. All right, it looks like there aren't any questions. Then I was happy to be here with you today. See you next time. Bye. How to finish it? Yes, here we go.